What if I told you that a single drag racer from Illinois outsmarted General Motors' entire engineering department and built a naturally aspirated small block Chevy that made 800 horsepower? Something Chevrolet's own engineers said was impossible. Not with nitrous, not with a supercharger, not with a turbo. Just pure naturally aspirated power from 500 cubic inches. That's 1.6 horsepower per cubic inch. A number that would make Formula One engineers take notice. And here's the thing, this wasn't some backroom myth or barroom legend. This actually happened, and the ripple effects of what one man did in a shop in rural Illinois are still being felt in motorsport today. Picture this. It's 1992, and the NHRA Pro Stock class is in absolute chaos. Teams are spending millions trying to squeeze every last horsepower from their engines, but they're all hitting the same wall. 700 horsepower seemed to be the absolute ceiling for a naturally aspirated engine under Pro Stock rules. The best engine builders in the country, names like Rear Morrison, Joe Lepone, and Bob Glidden, were all stuck in the same performance window. Then Warren Johnson showed up with something that changed everything. His competitors could hear the difference before they could even see it. Johnson's engine had a distinct, almost violent bark that separated it from every other small block on the property. When he uncorked it on the starting line, other teams would literally stop what they were doing to watch. The sound alone told you something different was happening under that hood. This is automotive ancestry, and I spend way too much time thinking about the engineering brilliance behind motorsport's greatest breakthroughs. If you're someone who geeks out over the stories of racers who rewrote the rulebook through sheer intelligence and innovation, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. This is the story of Warren the Professor Johnson and the secret small block that rewrote the rules of naturally aspirated performance. It's a tale of one man's obsession with airflow, his flat-out rejection of conventional wisdom, and how he built an engine so revolutionary that it dominated professional drag racing for an entire decade. Johnson didn't just beat his competitors. He made their engines obsolete overnight. Now, to understand the magnitude of what Johnson actually pulled off, we need to travel back to the golden age of pro stock drag racing. The late 1980s and early 1990s were a time of incredible innovation in the class. NHRA had strict rules. Engines had to retain the basic architecture of production motors. They had to be naturally aspirated, and they were limited to 500 cubic inches of displacement. No power adders allowed. This wasn't Top Fuel where you could throw 10,000 horsepower at the problem. This was a thinking man's game where fractional improvements in efficiency translated to wins and losses measured in thousandths of a second. The conventional approach was pretty straightforward. Take a big block Chevy, Ford, or Chrysler engine, bore it out to the maximum allowed displacement, add the best aftermarket cylinder heads money could buy, and tune it within an inch of its life. The big blocks had inherent advantages. Larger bore spacing allowed for bigger valves. Their tall deck heights accommodated long strokes, and their robust bottom ends could handle the stress of sustained high RPM punishment. Small blocks were considered completely inferior for this application. Their compact architecture, while great for street cars, seemed to impose hard limits on ultimate power production. Chevrolet's small block V8, introduced in 1955, had become the most successful engine design in automotive history. By 1992, millions had been produced. The aftermarket had developed every conceivable performance part for it. But even with the best available components, small blocks in pro stock typically made 100 to 150 horsepower less than their big block counterparts. The limiting factor was always the same: cylinder heads. The small block's 4.4-inch bore spacing, which is the distance between cylinder centerlines, constrained valve size in a very real and mathematically unforgiving way. Chevrolet's best production heads topped out at 2.02-inch intake valves, with some rare versions using 2.08-inch valve. The aftermarket had pushed this slightly further, but physics seemed to impose hard limit. Larger valves would shroud against the cylinder walls, disrupting airflow. The ports could only be made so large before they broke through into the water jackets or push rod passages. Every expert agreed. Small blocks were great for their size, but they'd never match big block power in a displacement-limited class. Warren Johnson disagreed. And unlike most people who disagree with conventional wisdom from a barstool, Johnson had the engineering background to actually do something about it. Here's what most people don't realize about Warren Johnson. He wasn't your typical drag racer. While many successful racers were talented mechanics who learned through trial and error, Johnson approached racing like an aerospace engineer approaches aircraft design. He'd earned his nickname, the Professor, not just because he wore glasses and looked scholarly, but because he had genuinely taught himself fluid dynamics, thermodynamics, and material science. His shop in Sugar Grove, Illinois looked more like a research laboratory than a race shop. He had built his own flow bench before most people even knew what a flow bench was. He wrote his own computer programs to model port shapes and valve events. While other teams were guessing based on experience and feel, Johnson was calculating based on data and physics. And that distinction, that fundamental difference in methodology, is what made everything that followed possible. The project that would revolutionize pro stock began with a simple but enormously powerful question. What if everyone was wrong about small blocks? Johnson had been racing a big block Oldsmobile with moderate success, but he saw an opportunity that everyone else had missed entirely. The small block's compact size meant less rotating mass. Its shorter stroke meant it could rev higher. If he could solve the airflow problem, he could build an engine that accelerated faster than any big block in the class. But solving that airflow problem meant reimagining the cylinder head from absolute scratch. Johnson's first breakthrough came from studying the relationship between port shape and flow velocity. Conventional wisdom said bigger ports flowed more air. Johnson discovered this was only partially true, and in some cases, outright wrong. Port velocity was equally important, especially at low and mid-lift valve positions where the valve spent most of its time during the cam event. A smaller, properly shaped port could actually flow more air than a larger, poorly shaped one. Look, it's like the difference between a garden hose and a fire hose at low pressure. The garden hose might have higher velocity even though it moves less total volume, and velocity is what fills the cylinder on a high-revving engine. He spent months analyzing every production and aftermarket small block head available. He flowed them at every possible angle with different valve jobs, various port modifications. He filled notebooks with data that would have bored most racers completely to tears. But buried in those numbers, Johnson found patterns that everyone else had missed entirely. The key wasn't just port size or valve size in isolation. It was the relationship between port cross-section, valve curtain area, and chamber shape. Get these three elements working in harmony, and airflow increased dramatically. Ignore the relationship between them, and you were just guessing expensively. Here's where it gets really interesting. Johnson realized he couldn't just modify existing heads to achieve what he wanted. The modifications required were so fundamental, so structural in nature, that no amount of porting, grinding, or reshaping existing castings would get him where he needed to go. He needed to start from absolute scratch. This meant designing and manufacturing his own cylinder heads, a process that would cost hundreds of thousands of dollars and require capabilities that most race teams simply didn't possess and had never needed to develop. Johnson didn't flinch at the scale of the challenge. He invested in CNC machines at a time when most race shops were still using hand grinders and die grinders guided by feel. He taught himself CAD programming on systems that were primitive by today's standards but revolutionary in that context. He built relationships with foundries that could cast his designs in the specific alloys he needed. While his competitors were on the phone ordering parts from catalogs, Johnson was on the phone ordering raw aluminum billet. While they were assembling, he was designing. The difference sounds small. The results were anything but. The heads Johnson developed were unlike anything the racing world had seen up to that point. The intake valves measured 2.30 inches, massive by small block standards and well beyond what anyone in the industry considered physically possible. To put that in genuine perspective, Chevy's own engineers had determined through their own testing and calculations that 2.08 inches was the absolute practical maximum for a small blockhead. Going larger would supposedly shroud the valve against the cylinder bore and actually reduce flow rather than increase it. Johnson proved them spectacularly wrong by completely reimagining the combustion chamber shape itself. He moved the spark plug location, altered the valve angles, and created a chamber geometry that unshrouded the valves at high lift while simultaneously maintaining excellent quench characteristics for efficient combustion. The intake ports were equally revolutionary in their design philosophy. Instead of following the traditional small block port shape, which curved dramatically inward to avoid the push rod passage in the head, Johnson's ports took a dramatically straighter path toward the valve. He achieved this by using offset rocker arms that physically relocated the push rod position, giving the port the clearance it needed to travel more directly. The ports were actually smaller in cross-section than many contemporary aftermarket heads, which sounds counterintuitive until you understand the velocity principle Johnson had built his entire design around. At 0.800-inch lift, Johnson's heads flowed over 400 cubic feet per minute, numbers that rivaled or matched the best big blockheads available at the time. The exhaust side received equal and meticulous attention. Johnson discovered through his flow bench work that most small blockheads suffered from fundamentally poor exhaust port design. The ports were typically too large, killing the velocity needed for strong cylinder scavenging and creating reversion problems that robbed power at high RPM. His exhaust ports were physically smaller than many production heads, but featured a unique D-shaped cross-section design that maintained velocity throughout the port while simultaneously improving overall flow. The exhaust valves, at 1.60 inches, were actually smaller than many production heads, but they flowed dramatically better because the port guiding air to and past them was finally doing its job correctly. But airflow, as impressive as Johnson's numbers were, represented only part of the equation he was solving. He understood deeply that making power required more than just moving air efficiently through the engine. You had to burn fuel with maximum efficiency and then convert that combustion pressure into crankshaft rotation with minimum loss. His heads featured carefully designed combustion chambers with optimal quench areas precisely calculated for his bore size and expected compression ratio. The quench, which is the tight clearance between the piston crown and the cylinder head surface at top dead center, created turbulence that improved mixture motion and combustion speed dramatically. Johnson spent countless hours optimizing chamber volume and shape to achieve compression ratios exceeding 14.1 to 1 while still avoiding detonation on the racing fuel of the era. The camshaft profile was equally critical to making the entire system work together. Now, you might be thinking that cam selection is pretty straightforward for experienced engine builders. Just buy the most aggressive grind available and make it work. Johnson understood that this approach was exactly why his competitors were limited. He didn't buy off-the-shelf cams. He designed his own profiles using computer modeling software he had developed himself, coding the valve motion mathematics from first principles. The cam had to work in perfect harmony with the heads, opening the valves at precisely the right rate and at precisely the right timing to take full advantage of his port flow characteristics at the specific RPM range where his engine made its power. His cam shafts featured extremely aggressive ramp rates that the industry hadn't seen before in this application. The valves accelerated off their seats faster than anything his competitors were running, which required an entirely upgraded valve train to survive. Titanium valves replaced steel ones to reduce reciprocating mass. Tool steel rocker arms replaced the stamped steel units used in lesser build. Valve springs capable of maintaining control past 10,000 revolutions per minute were sourced and tested extensively. The entire valve train was a system, and Johnson treated it as exactly that, designing each component around the demands of the others. The bottom end of Johnson's engine was a masterpiece of meticulous preparation rather than exotic or unusual components. He started with a production GM bow tie block, a race-oriented variant of the standard small block casting that had been available for years. What made Johnson's block special wasn't what it was made of, but what he did to it. Every surface was precision-machined to tolerances that were extraordinary for the era. The cylinders were bored and honed using specific techniques and stones that created an optimal crosshatch pattern for ring sealing. The crankshaft, a forged steel unit, was balanced to a level of precision that required equipment most shops didn't own. The connecting rods were made from 4340 steel and shot-peened for fatigue strength. The pistons, custom forgings, featured a crown design that worked synergistically with Johnson's combustion chamber geometry rather than simply fitting inside it. Assembly was where Johnson's methodical and almost obsessive approach really showed itself in the finished product. Every component was measured, documented, and selected for optimal clearances based on calculated rather than estimated operating conditions. Bearing clearances were set differently for each journal based on oil flow calculations specific to his oiling system design. Ring gaps were customized for each cylinder position based on expected temperature differences between front and rear cylinders. Johnson even developed his own assembly lubricants, working with additive manufacturers to create specific blends that would protect components during the critical initial startup period before the oil system was fully pressurized and circulating. The induction system was yet another area where Johnson innovated beyond what anyone had attempted in pro stock. While most pro stock racers were using tunnel ram intakes with carburetors mounted high above the engine in a configuration that had become essentially universal in the class, Johnson developed a unique design that positioned the carburetors lower and closer to the engine. This improved airflow distribution between cylinders dramatically, eliminating the front-to-rear imbalance that plagued conventional tunnel ram designs. He worked directly with Holley to develop custom metering blocks and air bleeds specific to his engine's fuel requirements that were themselves specific because his engine breathed so differently from every other engine in the class. The fuel curves were mapped with unprecedented precision using exhaust gas analyzers and data logging equipment that Johnson had adapted from industries that had nothing to do with motorsport. He was pulling technology from places his competitors weren't even looking, applying instrumentation principles from industrial process control and aerospace testing to problems that drag racers had always solved through intuition and experience. When Johnson first fired up his 800 horsepower small block in early 1992, even he was surprised by the result. The engine produced peak power at 9,200 revolutions per minute, nearly 1,000 revolutions per minute higher than most comparable big blocks. Torque peaked at 7,500 revolutions per minute at over 520 pound-feet. But the real advantage that would translate to wins on the racetrack was the power band's width and character. While big blocks typically had relatively narrow power bands that required near-perfect shift points from the driver to maintain momentum, Johnson's small block pulled hard from 7,000 revolutions per minute all the way to 9,500 revolutions per minute. This meant he could be slightly less precise with his shifts and still maintain strong acceleration throughout the run. In a class where races were decided by thousandths of a second, this consistency advantage was worth as much as the raw horsepower number alone. The first time Johnson showed up at an NHRA national event with his new combination, the reaction from the paddock was widespread skepticism bordering on disbelief. Pro stock had always been dominated by big blocks in the hands of well-funded factory-backed teams. Many in the pits thought Johnson was sandbagging, running slower than the car could go to hide his capability until eliminations. Others whispered that he must have some kind of illegal advantage hidden somewhere in the engine that tech inspection hadn't found yet. Tech inspectors tore his engine down after his first win, pulling the heads, measuring the bore, checking the stroke, verifying the displacement. It measured exactly 500 cubic inches. No power adders, no exotic fuels, nothing outside the published rulebook. Just superior engineering dressed up to look like a regular small block Chevy. Here's what most people don't realize about what was actually going wrong for everyone else. The answer lay in their fundamental approach to engine building at the conceptual level. Most teams in pro stock at that time were what Johnson would later call assemblers. They bought the best parts available from the best suppliers money could reach, and they bolted them together with genuine skill and reasonable precision. Johnson was something fundamentally different. He was a designer. He understood that optimal performance came not from the best individual components but from components designed specifically to work together as a complete and coherent system. His heads weren't just good heads that happened to be installed on his engine. They were heads designed specifically for his bore size, his stroke, his target RPM range, and his specific application. His camshaft wasn't just aggressive because aggressive was good. It was mathematically optimized for his specific port flow curves at specific valve lift increment. The competition's response was predictable and immediate. They tried to copy Johnson's approach, or at least his parts, as quickly as they could arrange it. But reverse engineering his heads proved nearly impossible even for teams with significant resources. Even when competitors managed to obtain castings through various means, they couldn't replicate his success on the racetrack. The ports could be physically duplicated through careful measurement, but the subtle details that made them work, the precise valve job angles, the specific chamber modifications, the exact surface finishes in critical flow areas, these required deep knowledge that couldn't be obtained simply by looking at parts under good lighting. Johnson had spent years developing his understanding of airflow principles. Copying his parts without understanding the principles behind them was, as he later said himself, like trying to copy a symphony by looking at the shape of the orchestra. But the real story here wasn't just the horsepower number, impressive as it was. It was how Johnson's engine fundamentally changed pro stock racing as an institution and as a discipline. Within 2 years, small blocks went from being considered also-rans in a big block world to being the dominant force in the class. Other manufacturers scrambled to develop their own high-flowing small blockhead. The aftermarket exploded with new designs claiming to match or approach Johnson's flow numbers. The entire industry shifted its fundamental focus from displacement as the primary variable to efficiency as the primary target. That shift, from thinking about cubic inches to thinking about cubic feet per minute, was Johnson's most enduring contribution. Johnson's success forced NHRA to reconsider their rules and their approach to competitive balance in the class. The sanctioning body had always tried to maintain parity between makes and engine configurations. With Johnson dominating in his Pontiac-bodied Chevy-powered car, they implemented new weight breaks and rules adjustments aimed at leveling what had become an increasingly lopsided competitive landscape. But Johnson adapted faster than the rules could change, and that adaptability itself was a product of his systematic approach. When they added weight to his car, he found more power. When they restricted certain modifications, he innovated in areas the rules hadn't yet thought to address. The regulations were always chasing him, never quite catching up. The 1993 season was Johnson's masterpiece and the clearest demonstration of his advantage over the field. He won 10 national events and clinched his first NHRA Winston Championship in dominant fashion. His small block was now making closer to 825 horsepower, and he'd refined his chassis setup to take full advantage of the engine's specific power delivery characteristic. At the U.S. Nationals, NHRA's most prestigious event, Johnson didn't just win. He reset both ends of the national record in a single run. His 6.988-second pass at 196.24 miles per hour was the first pro stock pass under 7 seconds at a national event. The crowd reaction was visceral and immediate. Something historic had just happened, and everyone present knew it. Trackside, the advantage was visible to anyone paying attention. Johnson's car left the starting line differently from big block cars in a way that was immediately obvious to experienced eyes. Instead of the brutal and immediate torque hit that characterized big blocks off the line, Johnson's car accelerated progressively and relentlessly. The small block's rising power curve was perfectly matched to the increasing load as the car gained speed and the tires began generating traction. By half-track, he'd typically have a 2 to 300 thousandths of a second advantage over his competition. In a class where races were commonly decided by margins smaller than a blink, this was domination, not just victory. The dyno numbers told only part of the story, though, and perhaps not even the most important part. Johnson's engine made 800 horsepower, yes, but it did so while being dramatically more reliable than engines making 100 horsepower less. The small block's shorter stroke meant less stress on the reciprocating assembly at any given RPM. The lower rotating mass meant less harmonic vibration building up through the engine at sustained high speed. Johnson could run entire events without opening the engine while competitors were rebuilding between rounds, replacing pistons, checking bearings, testing springs. This reliability advantage compounded his performance advantage in a way that raw horsepower numbers couldn't fully capture. Let me put that reliability in genuine financial perspective. In professional drag racing at that level, engines were typically rebuilt after every few runs under stress. Pistons were replaced, bearings were measured and often changed, valve springs were tested for fatigue. It was not uncommon for a well-funded pro stock team to go through a dozen engines or more in a single season. Johnson's engines would run entire race weekends, both qualifying sessions and the full elimination ladder on race day, without being substantially touched between runs. He'd check valve lash and change the oil, but the bottom end stayed sealed and intact. This wasn't fortunate accident. It was engineered reliability, designed in from the beginning rather than hoped for. The financial implications of that reliability were genuinely staggering when you worked through the math. A competitive pro stock team at that time could easily spend $500,000 on engines alone in a single season, between the initial builds, the rebuilds, the parts replacements, and the inevitable catastrophic failures that came with running at the absolute edge of what components could survive. Johnson's program, despite the enormous initial development costs he'd absorbed years earlier, operated on a fraction of that ongoing expense. He wasn't buying parts constantly. He was making them once and making them right. He wasn't guessing about what had failed and why. He was calculating from data what would happen and when. While other teams threw money at the problem hoping something would stick, Johnson threw knowledge at it and knew exactly what would stick and why. But here's the kicker that most people find genuinely surprising when they first hear it. Johnson didn't keep his advantage secret out of greed or competitive spite. He actually sold engines to other racers at extraordinary prices that reflected their extraordinary performance. A complete Johnson racing engine in 1994 cost upward of $80,000, which translates to roughly $160,000 in today's money. And racers paid it gladly, sometimes waiting years on a list for the privilege. Even with Johnson's engines installed in their cars, though, they couldn't consistently beat Johnson himself. And this fact reveals something profound about the nature of his real advantage. The engine was only one part of what separated him from the field. His actual edge was understanding how to make it work in the car, how to tune it for specific conditions on specific days, how to extract every available fraction of performance through decisions made in real time during an event. The technical deep dive into Johnson's cylinder head design reveals why they were so thoroughly revolutionary and why they couldn't simply be copied without understanding. The intake port entrance was radiused to a specific mathematical curve that minimized boundary layer separation, the phenomenon where airflow detaches from the port wall and becomes turbulent rather than laminar. The port floor had a slight upward curvature near the valve that Johnson called the ski jump effect, which helped direct the incoming air charge toward the valve at the optimal angle for maximum curtain area utilization. The bowl area, where the port transitions and opens up behind the valve head, featured a unique three-angle configuration that Johnson had developed through literally thousands of hours of individual testing on his flow bench. The valve seat angles themselves were unlike anything else in pro stock at the time. Rather than the conventional 45-degree cuts that had been standard practice for decades, Johnson used a proprietary combination of angles that he'd calculated through analysis of flow behavior at specific valve lift increments. The combustion chamber design incorporated principles drawn from aircraft engine research that Johnson had spent significant time studying. He had obtained technical reports and papers from Pratt & Whitney and Rolls-Royce about combustion dynamics in high-performance aircraft engines and applied concepts like squish velocity, mixture motion control, and flame front geometry that were essentially foreign to automotive racing applications. The spark plug was positioned not where it was most convenient to install, but where analysis indicated an optimal flame front would propagate most evenly across the chamber at the compression ratios he was running. The piston crown geometry was dished in specific areas that Johnson had mapped through both calculation and testing to create controlled turbulence during the compression stroke that complemented his combustion chamber's flow characteristics. Even the valve materials received careful and specific attention that went well beyond what other teams were doing. While most racers of the era used standard titanium valves for their weight advantage, Johnson experimented with different specific alloys for different applications and operating conditions. He discovered that certain titanium alloy formulations performed better at the extreme RPM he was targeting, while specialized steel alloys offered superior heat dissipation characteristics for applications that prioritized endurance over peak RPM. The valve stems were gun-drilled to remove weight in the stem without sacrificing the torsional strength the valve needed to survive repeated high-speed operation. The oiling system in Johnson's engine received the same systematic treatment as every other subsystem. He modified the priority main oiling circuit to deliver pressurized oil to the main bearings first, then the cam bearings, and finally to the lifters and valve train, ensuring that the components under the greatest load always had oil pressure before anything else received it. Oil flow restrictors were installed in strategic locations throughout the system to prevent overoiling areas that didn't need or benefit from excessive lubrication, keeping oil in the pan and available where it was actually needed. The oil pan itself was extensively baffled with trap doors and scrapers that prevented oil from sloshing away from the pickup under the sustained high G acceleration that pro-stock cars experience on every single run. Johnson even developed his own specific oil formulations working directly with Mobil, creating blends with specific viscosity curves and additive packages calibrated for his engine's operating conditions. The cooling system received similarly obsessive attention to detail. Johnson had identified through his temperature measurement work that most small blocks suffered from localized hot spots developing around the exhaust valve areas, where heat rejection demands were highest and coolant flow was often poorest due to the geometry of the casting. He modified the water jacket configuration in his heads to dramatically increase coolant flow velocity in these critical areas. The head gaskets were custom-manufactured items with specific cooling passages designed to match his head modifications rather than the production block's original layout. Even the water pump impeller was modified with a revised geometry that increased flow volume without inducing the cavitation that can destroy pump efficiency at high impeller speed. The ignition system was another area where Johnson pushed technology well ahead of where the rest of pro stock was operating. While most pro-stock cars of the early 1990s still relied on magneto-ignition for its simplicity and reliability under racing conditions, Johnson developed one of the first truly successful electronic ignition systems in the class in collaboration with MSD. This system could vary ignition timing dynamically based on both RPM and engine load conditions, allowing Johnson to run more aggressive timing curves at partial load without the detonation risk that a fixed curve would have required him to guard against. The system ultimately incorporated individual cylinder timing control, a capability that was genuinely revolutionary for the era, allowing Johnson to optimize the ignition event for each cylinder independently based on the flow characteristics he knew each cylinder's head port delivered. Johnson's data acquisition capability was perhaps his single largest competitive advantage over the medium term, the advantage that allowed him to continue improving while everyone else was simply trying to understand where they currently stood. In 1992, the vast majority of race teams relied on printed time slips from the track's timing system and feedback from their driver to understand what was happening during a run. Johnson had accelerometers, pressure transducers, and thermocouples installed throughout his car, measuring what was happening at every moment from the instant the throttle opened to the instant the parachutes deployed. Clutch slip rate, tire shake character, aerodynamic downforce changes, oil pressure fluctuations, coolant temperature gradients between cylinders, everything was recorded with a time resolution that made it actionable. After each run, Johnson would download the data to his laptop and analyze it against his mathematical models of what should have happened under those conditions. The comparison between predicted and actual behavior guided every tuning decision he made with a precision that pure experience couldn't match and that time slips alone could never provide. This information loop, measure, analyze, predict, adjust, measure again, was what separated his development rate from everyone else's. While competitors were making changes based on what felt better, Johnson was making changes based on what calculated better. The subjective impressions of experienced people are valuable, but they are not the same thing as measurement, and Johnson understood this at a time when most of his competitors didn't even know there was a difference worth caring about. The transmission and clutch setup were calibrated with the same systematic precision to work specifically with the small block's unique power delivery curve rather than being set up generically and then adjusted based on track result. Johnson used a Liberty 5-speed manual transmission with custom gear ratios that he had calculated mathematically to keep the engine operating within its optimal power band throughout every phase of the run from launch to the finish line. The clutch was a 3-disc carbon fiber unit that Johnson tuned with different spring pressures and lever ratios arrived at through analysis rather than trial and error. He discovered through his data that the small block's progressive power delivery actually allowed for less aggressive clutch engagement settings than big blocks required, which had the secondary benefit of reducing the tire shake events that robbed time and consistency from virtually every pro stock car of that era. The impact on the broader industry was immediate in some ways and deeply lasting in others. Within 3 years of Johnson's breakthrough becoming impossible to ignore or explain away, every major cylinder head manufacturer had devoted significant engineering resources to developing high-flow small block designs directly inspired by his approach. Companies like Brodix, Dart, and AFR created heads capable of flowing 400 or more cubic feet per minute in configurations that would have been considered impossible before Johnson demonstrated what was achievable. The aftermarket responded with new valve train components capable of handling the higher spring pressures and sustained RPM that Johnson's approach demanded. Piston manufacturers developed new forgings specifically designed to work with the higher compression ratios these new heads made possible without detonation on available fuels. But the real revolution, the lasting one that persists to this day, wasn't in the parts. It was in the approach. Johnson had proven irrefutably that intelligent, systematic engineering could overcome brute financial force. His success inspired a generation of engine builders to fundamentally think differently about what they were doing and why. Instead of making parts bigger and hoping for more power, they started making parts better through understanding. Computational fluid dynamics, once exclusively the province of aerospace and automotive OEM engineering departments, began finding its way into high-end racing development. Flow benches went from exotic and expensive luxuries to mandatory minimum equipment for any serious engine development program. The thinking changed because one man had proven conclusively that thinking was worth more than spending. The personal rivalry between Johnson and his closest competitors became the stuff of genuine legend in the class. Bob Glidden, the dominant Ford racer who had defined pro-stock excellence through the 1980s, spent millions attempting to match Johnson's power output after it became clear that Johnson wasn't going away. He eventually succeeded in closing the gap, but only by adopting Johnson's systematic, engineering-led approach rather than continuing with the experience-based methods that had made him successful earlier. The two engaged in a technological arms race through the mid-1990s that pushed pro-stock performance to levels that the class's founders genuinely hadn't imagined possible. By 1995, both were running in the 680s at over 200 miles per hour, performance that would have placed them in top fuel company just a decade earlier. Johnson's influence ultimately extended far beyond pro-stock, and even beyond drag racing itself. His cylinder head design philosophy influenced performance development in NASCAR, where the naturally aspirated efficiency he pioneered became increasingly important as restrictor plate racing demanded maximum power from limited airflow. Marine racing applications adopted his port design principles for high RPM outboard engines where similar airflow constraints applied. The principles he developed through years of patient, systematic work, optimizing port velocity, managing combustion dynamics through chamber geometry, treating the engine as a completely integrated system rather than a collection of individual parts, became standard practice across all forms of motorsport at the professional level within a decade of his breakthrough. Even Formula One teams quietly studied Johnson's published work and interviewed people who had worked with him, applying his naturally aspirated efficiency concepts to their own development programs during the naturally aspirated V10 era of the late 1990s. The specific CFD techniques Johnson pioneered using his primitive by today's standards computer models were recognizable in the methodology of modern F1 engine development programs. One man in a shop in Illinois had influenced the most technically sophisticated motorsport on Earth. That is not a small thing. The 1996 season saw Johnson win his fourth championship in 5 years of competition with his small block combination. His engine was by then making over 850 horsepower, still completely naturally aspirated, still exactly 500 cubic inches of displacement. The power per cubic inch ratio had reached 1.7, a figure that had seemed not just difficult but genuinely impossible just 5 years earlier when he'd started this journey. To put this achievement in proper context, a modern NASCAR Cup engine makes approximately 1.6 horsepower per cubic inch with the benefit of vastly more advanced materials, superior manufacturing precision, advanced simulation tools, and decades of accumulated development knowledge. Johnson achieved better specific output with 1990s technology, 1990s materials, and computer tools that modern engineers would consider embarrassingly primitive. He achieved it through superior understanding of the fundamental physics governing how air moves and how combustion works. By 1998, Warren Johnson had accumulated 6 NHRA Pro Stock Championships and 81 national event victories, numbers that placed him among the most successful drivers in the class's history. His small block combination had evolved through multiple generations and iterations, each one more powerful and more reliable than the last. He'd pushed the acknowledged boundaries of what was possible with pushrod-actuated valve trains, achieving specific power outputs and sustained RPM levels that engineering textbooks of the era said would destroy a pushrod engine through valve float and spring fatigue. Yet his engines survived those conditions, thrived under them, and dominated competitions populated by engines built by the most experienced and best-funded teams in the sport. The cost of this sustained success was enormous, though not primarily in financial terms. Johnson had invested over $2 million of his own money in the development program over its full arc, money that came not from corporate sponsors in the early years but from his own racing income and savings. He'd sacrificed time with his family that he has spoken about with genuine regret in later years, working 18-hour days for years on end during the development phase and maintaining brutal schedules throughout the championship years. His health reflected the cumulative stress of sustained extreme effort over a long period. But for Johnson, the driving motivation was never primarily about the championships or the prize money or the recognition, as gratifying as all of those things were. It was about proving what was possible when engineering principles were applied correctly and completely to a problem that everyone else was approaching through intuition and experience. The modern perspective on what Johnson achieved makes it even more remarkable rather than less. Today's pro stock engines produce more than 1,500 horsepower from the same 500 cubic inch displacement limit, but they do so with the benefit of billet aluminum blocks machined from solid material, pneumatic valve actuation systems that replace mechanical springs, ceramic thermal barrier coatings on critical surfaces, and development programs supported by advanced CFD simulation and 3D printing of prototype components. Johnson achieved half that power output using cast iron blocks, mechanical steel valve springs, no surface coatings of any significance, and computer tools that would be considered toys by modern simulation standards. He achieved it through superior understanding of the physics involved, and that distinction matters enormously. Current pro stock champion Erica Enders has credited Johnson publicly as the father of the modern pro stock class in terms of its technical character. Warren changed everything, she has said in multiple interviews. Before him, it was about who could afford the best parts that were available. After him, it was about who could think the best thoughts about what the parts should be. He made it a thinking person's class, and it's never gone back to being anything else. Greg Anderson, who now holds many of Johnson's former records and has won multiple championships himself, learned his craft working directly for Johnson during the peak years. Everything I know about how engines actually work at a fundamental level, I learned from Warren, Anderson has stated publicly on multiple occasions. He didn't just build engines. He understood them at a level that most people in racing have never approached. The engineering principles Johnson pioneered remain genuinely relevant and actively influential today, not as historical curiosities but as working foundations of current development practice. His emphasis on port velocity as a primary design variable rather than simply port cross-sectional area influences every serious cylinder head design being developed for naturally aspirated racing applications. His systematic approach to engine development, treating every component as part of an integrated system with defined relationships to every other component, is now the universal standard in professional motorsport rather than one man's idiosyncratic method. His use of data acquisition and quantitative analysis to guide development decisions predated the current data-driven culture of motorsport by more than a decade and established the template that everyone now follows as though it were obvious and had always been done this way. In many ways, Warren Johnson was engineering 21st-century engines with 20th-century tools, driven by 21st-century thinking about what rigorous methodology could accomplish when applied to problems that everyone else was treating as matters of experience and intuition. Perhaps the most resonant aspect of Johnson's story is how one individual with limited resources managed to out-engineer a massive corporation with virtually unlimited engineering capability. General Motors had thousands of degreed engineers, effectively unlimited development budgets, advanced testing facilities, and decades of institutional knowledge about their own engine architectures. Warren Johnson had a shop in rural Illinois, a small team of trusted people, his own hard-won intelligence, and an absolute refusal to accept that something was impossible simply because everyone with credentials said so. Yet he built better Chevy engines than Chevrolet could build, and he proved it publicly every weekend throughout an entire decade of racing. This story resonates so deeply because it proves something that people need to believe is true, that innovation genuinely doesn't require massive resources or institutional backing. It requires insight into what the real problem actually is, determination to solve it through understanding rather than through brute force, and the intellectual courage to challenge conventional wisdom even when everyone with apparent authority is telling you that you're wrong. The specific innovations Johnson developed remain embedded in the engineering practice of motorsport at every level. His combustion chamber design has been refined with better tools but not fundamentally reconceived. The port design philosophy he pioneered is the foundation on which every serious racing head built today is designed. His approach to valve train dynamics, using precisely controlled aggressive cam profiles designed around specific port flow characteristics rather than general performance targets, established the template that all serious engine builders now follow as standard practice. Even his data analysis methodology, revolutionary and somewhat lonely in 1992, is now simply how professional motorsport operates at every level from pro stock to Formula One. Warren Johnson's greatest contribution to racing was never any single innovation, as impressive as each individual breakthrough was. It was proving definitively and repeatedly under competitive pressure that racing success came from understanding the physics of what you were doing, not just from effort or resources or experience. He showed that the winner wasn't necessarily who worked the hardest or spent the most or had the most years behind them. It was who thought the deepest about the actual problem and pursued the answer with the most systematic rigor. In an era of increasingly complex technology in every field, this lesson becomes more relevant with every passing year, not less. The secret small block that made 800 horsepower was never really about secrets at all. It was about applying scientific principles to engineering problems with more care and more rigor than anyone else was bringing to the same problems. It was about questioning assumptions that everyone else had accepted without examination and testing hypotheses that everyone else had dismissed without analysis. It was about one man's absolute refusal to accept that something was impossible just because everyone with apparent authority said so. Warren Johnson didn't just build a better engine. He built a better way of building engines, and every naturally aspirated racing engine built with serious intent since 1992 carries his influence whether the people building it know his name or not. Today, Warren Johnson is retired from driving competition but remains involved in engine development through his shop, which continues producing engines for select customers at prices that reflect both their performance and the decades of knowledge crystallized inside them. The waiting list is measured in years, not months, and the prices are extraordinary by any measure. But the racers who wait and who pay do so because a Johnson engine represents something that money alone genuinely cannot buy: the accumulated understanding of a lifetime spent thinking more carefully about airflow and combustion than almost anyone else in the history of the sport. The small block V8 that started this entire revolution sits in Johnson's personal collection, a monument to what becomes possible when engineering excellence meets the kind of competitive drive that refuses to accept that something cannot be done. It doesn't look particularly special to the untrained eye. Just another small block Chevy, a common sight at any car show or racetrack in America. But to those who understand its history and its significance, it represents something profound. This engine didn't just win races. It changed how races are won, how engines are developed, how the entire sport thinks about the relationship between knowledge and performance. That is a legacy that outlasts any championship, any record, and any individual career. And that is why Warren Johnson's story deserves to be told and told again. What if I told you that for decades, Detroit's biggest automakers have been leaving horsepower on the table, not because they couldn't find it, but because they chose not to? That the solution to unleashing 20, 30, even 40% more power from their engines has been sitting in junkyards across America, waiting for someone smart enough to see what the factory engineers deliberately ignored. Picture this. It's 1987 in a garage outside Dayton, Ohio. Mike Lersky, a mechanic who'd been turning wrenches since he was 14, is staring at a blown Buick Grand National engine on his lift. The owner wants it rebuilt, but Mike's looking at something that doesn't make sense. The intercooler, that critical component that cools the compressed air before it enters the engine, is tiny, pathetically small, like putting a drinking straw on a fire hose. He measures it, does the math. The factory intercooler can only dissipate about 60% of the heat it should. That means the engine is breathing hot air, killing power, increasing detonation risk, shortening engine life. General Motors, with all their engineers and million-dollar test facilities, built this thing. They knew exactly what they were doing. But here's where it gets interesting. This is automotive ancestry, and I spend way too much time thinking about how Detroit's engineers deliberately sandbagged their own engines and left real performance buried in junkyards across America. If you're someone who loves digging into the mechanical mysteries that automakers hoped you'd never figure out, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. This is the story of how independent mechanics across America discovered they could outsmart Detroit's bean counters with nothing more than a wrench set, a tape measure, and regular trips to the local junkyard. How they exposed a dirty secret the auto industry hoped you'd never figure out, that your engine was deliberately handicapped from the factory and the cure was often sitting in a scrapyard, pulled from a completely different vehicle. Look, this isn't conspiracy theory stuff. This is documented engineering history, and by the time we're done today, you're going to see your local junkyard in a completely different light. To understand why Detroit would deliberately cripple their own engines, we need to travel back to the 1960s. The horsepower wars were in full swing. Chrysler was dropping 426 HEMAs into anything that would hold them. Ford had the 427 Cobra Jet. Chevy was stuffing 454 big blocks into Chevelles. Power was everything. Insurance companies were starting to notice. So was the government. By 1971, two things happened that changed everything. Insurance rates for high-performance cars went through the roof. We're talking $3,000 a year in 1971 for a Plymouth Hemi Cuda, which was more than some people paid for their entire car. And the EPA started requiring emissions testing. Suddenly, automakers faced a dilemma they couldn't escape. They needed to keep building exciting cars to sell, but they couldn't make them too powerful or too dirty. Their solution was genuinely brilliant in a cynical kind of way. Build engines with potential, then deliberately restrict them. Use undersized carburetors, restrictive exhaust manifolds, tiny intercoolers on turbocharged engines, conservative camshaft profiles, mild ignition timing. That way, they could advertise reasonable horsepower numbers to keep insurance companies happy, meet emission standards, and still give enthusiasts an engine that could be awakened later by someone willing to do the homework. The accountants loved this approach for another reason entirely. Why spend money on a proper intercooler when a smaller one would technically work? Why use forged pistons when cast ones would survive at the restricted power level? Why install a performance camshaft when a mild one would do? Every dollar saved in production multiplied across hundreds of thousands of units became a significant line item on a quarterly earnings report. And here's the thing, the engineers who knew better were often powerless to argue against the math. Now, you might be thinking, surely the engineers pushed back. Surely someone in those design meetings said something. They did. And there are internal documents, some of which surfaced during litigation years later, that show engineers flagging inadequate cooling systems, restrictive intake designs, and suboptimal valve train geometry. Their concerns were acknowledged, documented, and then systematically overridden by product planners and financial analysts. The engineers built what they were told to build. The restrictions weren't accidents. They were specifications. So what was actually going wrong with these factory engines? Let's dive into the technical reality that Detroit didn't want you to understand. Take that Grand National engine Mike Lursky was staring at. The stock intercooler had about 47 square inches of core area. At 15 pounds of boost, which the engine was capable of generating, you need roughly 70 to 80 square inches minimum for proper heat dissipation. GM's engineers knew this. The calculation is completely straightforward. Ambient temperature plus boost pressure multiplied by 11 gives you charge temperature rise. Without adequate cooling, that compressed air entering the engine could be 250 degrees Fahrenheit instead of 100 degrees. Every 10-degree increase in intake temperature costs you about 1% power. But it's worse than that isolated number suggests. Hot air is less dense, so you're getting less oxygen per cylinder fill. Hot air increases the tendency toward detonation, so the computer pulls timing, costing more power. The engine runs richer to compensate, washing oil off cylinder walls and accelerating wear. GM saved maybe $40 per car using the smaller intercooler. Multiply that by 30,000 Grand Nationals built, and they saved $1.2 million. The performance cost was about 60 horsepower left on the table. 60 horsepower for $1.2 million in corporate savings. That's what you were dealing with every time you pressed the gas pedal. Here's what most people don't realize about what Mike Lursky did next. He'd been prowling junkyards for years with a trained eye, measuring things other mechanics ignored. He'd noticed something interesting sitting in a wrecked Thunderbird. The 1989 Thunderbird Super Coupe had an intercooler that was almost twice the size of the Grand Nationals unit. Different manufacturer, different mounting points, but the core itself was just aluminum tubes and fins doing a specific thermodynamic job. Physics doesn't care what badge is on the front of the car, and it definitely doesn't care about brand loyalty. He bought one for $75, spent a weekend fabricating mounting brackets and rerouting pipe. Dyno tested it with obsessive attention to detail, making sure every other variable stayed identical. Stock Grand National with the factory intercooler produced 235 horsepower at the wheels. Same car, same boost level, same fuel, same tune, just the Thunderbird intercooler, 284 horsepower. 49 horsepower for $75 and some fabrication work. Let that number settle for a second. Word spread through the Grand National community like wildfire. Within 6 months, Junkyard Thunderbird Super Coupes were being picked clean of their intercoolers. Ford probably wondered why there was suddenly such unusual demand for crashed Super Coupe parts. They never connected the dots publicly, but you can bet someone in Dearborn noticed the pattern. But intercoolers were just the beginning of what mechanics were uncovering. The real revelation came when they started doing what Detroit's engineers were specifically forbidden to do, looking at engines as interconnected systems that could borrow solutions from each other regardless of manufacturer loyalty or corporate boundaries. Here's an example that'll genuinely blow your mind if you've never heard this story before. The Chevrolet 350 small block is arguably the most produced V8 engine in history. Millions built, used in everything from work trucks to Corvettes, from ambulances to muscle cars. The factory heads on most 350s flowed about 170 cubic feet per minute at 500 lift on the intake side. Adequate for a truck motor making 200 horsepower in a half-ton pickup hauling lumber, but genuinely pathetic for any performance application where the engine needed to breathe at higher RPM. In 1993, a speed shop owner in Texas named John Lingenfelter discovered something that should have been obvious but somehow wasn't. The 1991 through 1995 GM truck 454 big blockheads, The ones from basic work trucks used in construction fleets and rental yards had ports that were surprisingly similar in overall sizing to small blockhead. Different bolt pattern, yes, but the combustion chambers were efficient, the valve sizes were larger, and the ports flowed significantly better than anything GM put on a performance small block. The stock 454 truck heads flowed 245 cubic feet per minute at 500 lift. That's a 44% improvement over stock 350 heads. These weren't expensive performance parts sitting behind a glass counter at a speed shop. These were heads pulled from 2-ton dump trucks and motorhomes that had lived hard lives moving dirt and hauling families across the country. Junkyards were absolutely full of them because nobody wanted erect dump trucks' cylinder heads. Until now. Lingenfelter spent months developing an adapter system, special intake manifold spacers, modified head bolt holes, custom pushrods to correct the geometry created by the dimensional differences between the block. When he was done, he had a proven system that let you bolt big block truck heads onto a small block. The cost was about $800 in adapter parts plus $200 for a pair of used truck heads from a junkyard. The results were staggering in a way that made engineers uncomfortable. A mild 350 with stock heads might make 325 horsepower. The same engine with adapted 454 truck heads produced 425 horsepower. Same displacement, same bottom end, same camshaft, just better breathing from heads that GM built for completely different applications and never intended to be combined this way. Let that sink in for a moment because this is where it gets really interesting. General Motors had the capability to make small block heads that flowed like this. They chose not to. They had the big block heads sitting right there in their parts catalog, being cast at the same foundries, shipped by the same suppliers. They never thought to adapt them for performance applications, or more accurately, they never wanted to. Because if the base small block breathed properly, what would they sell you as an upgrade? This is the question that unlocks the entire philosophy behind what Detroit was doing. The rabbit hole goes considerably deeper once you start pulling on these threads. Mechanics discovered that Ford's 460 truck engine had rocker arms with a 1.73 to 1 ratio compared to the standard 1.5 to 1 ratio used on most V8 applications across multiple manufacturers. These weren't racing parts sitting in a specialty catalog. They were heavy-duty truck components, overbuilt for reliability in commercial applications where a breakdown meant a missed delivery contract and an angry fleet manager. But that higher ratio meant more valve lift without changing the camshaft profile at all. More lift meant more airflow through the ports. More airflow meant more power on every single power stroke. The math was simple and the results were predictable once someone actually bothered to check the interchange. Those Ford rockers would fit on a Chrysler 440 with minor modifications, the kind of modifications any competent machinist could handle in an afternoon. Suddenly, Mopar guys were raiding Ford truck junkyards, which was a cultural crossing that would have seemed absurd in any other context. A set of 460 truck rockers cost maybe $50 used, sitting in a bin with other greasy small parts that most junkyard visitors walked right past. They'd add 20 horsepower to a 440 without touching anything else in the engine. No camshaft change, no headwork, no intake swap. Just better geometry on the valve train, courtesy of Ford's commercial truck division. Think about the genuine absurdity of this situation. Chrysler engineers developing the 440 in one building. Ford engineers developing the 460 in another building in another state. Neither team talking to each other, obviously. Both solving similar valve train durability problems in different ways. And it took shade tree mechanics to realize that Ford's solution to their problem could improve Chrysler's engine. The pattern kept repeating everywhere once you knew what to look for and were willing to ignore the brand loyalty that manufacturers spent millions cultivating. The throttle body from a 1988 through 1992 Camaro TPI system was 48 mm, restrictive enough to kill meaningful top-end power where the engine really wanted to breathe. But the throttle body from a 1994 through 1996 Impala SS was 52 mm, the same bolt pattern, the same TPS sensor mounting, the same electrical connections. Literally a bolt-on upgrade that added 15 horsepower to TPI Camaros without any other changes. Junkyards had hundreds of crashed Impalas from the same era because those cars were popular in urban markets and had a tendency to accumulate accident damage. $25 for a throttle body that GM should have installed from the factory on every performance application, but chose not to because product differentiation demanded keeping the Camaro slightly slower than it could have been. Now you might be thinking, okay, these are interesting anecdotes, but surely there's a limit to how far this cross-brand thinking actually went. Surely at some point the engineering differences between manufacturers created real barriers that couldn't be crossed with junkyard ingenuity. And that's a completely reasonable objection. Here's the thing though. The mechanics who built this entire movement weren't just randomly bolting things together and hoping for the best. They were doing careful measurement work, flow bench testing, and dyno validation that rivaled what factory engineering teams were doing with much larger budget. They just had something the factory engineers lacked: complete freedom to try anything. Then there were the truly creative swaps that exposed just how much performance Detroit was leaving on the table and how internationally distributed the solutions actually were. The Mazda RX-7 Turbo 2 intercooler became legendary in the DSM community. That's Diamond Star Motors, the joint venture between Chrysler and Mitsubishi that built the Eagle Talon and Mitsubishi Eclipse in a factory in Illinois. The stock DSM intercooler was a genuine joke among people who understood cooling efficiency. Tiny, inefficient, heat-soaked after a single dragstrip pass to the point where back-to-back runs produced meaningfully different power numbers because the first run cooked the intake charge for everything that followed. But the RX-7 intercooler had a massive core area, efficient end tank design, and excellent internal flow characteristics. It fit in the DSM chassis with minor bracket fabrication work that any competent welder could accomplish. Stock DSM with factory intercooler running 15 psi produced maybe 250 wheel horsepower before heat soak destroyed the numbers. Same car with an RX-7 intercooler produced 290 wheel horsepower, and it would repeat that number run after run without the heat soak degradation that made the stock system so frustrating at the track. The Mazda intercooler cost $100 at a junkyard. Mitsubishi wanted $800 for their upgraded intercooler that didn't even flow as well as the Mazda piece. And here's the kicker that really exposes the corporate thinking behind these decisions. Mitsubishi knew their intercooler was inadequate. This wasn't a surprise to anyone sitting in their engineering department. In Japan, the same basic car sold as the Lancer Evolution had a proper intercooler installed as standard equipment because Japanese enthusiast buyers were more technically sophisticated and would notice the difference immediately. But for the US market, they cheaped out on a component that cost maybe $60 more in production. That $60 savings cost their American customers 40 horsepower at the wheels and countless blown engines from detonation events caused by inadequately cooled intake charges running into the combustion chamber at temperatures that push the engine right to the edge of its knock threshold. The Ford guys discovered something equally mind-blowing when they started actually measuring what they had versus what was theoretically possible. The E7TE heads from 1987 through 1993 5.0-liter trucks flowed terribly in stock form, everyone agreed on that. But they had something special hidden inside the casting that nobody had bothered to look for. The combustion chamber design was actually superior to the performance GT40 heads that Ford charged significant premium money for in their performance parts catalog. The spark plug location, the quench area, the valve shrouding geometry, all better on the plain truck heads than on the fancy GT40 heads that Ford was aggressively marketing to Mustang enthusiasts. A clever mechanic in California named Tom Moss figured out that if you ported the truck heads properly, focusing specifically on the bowl area beneath the valve seats and the short turn radius where airflow was losing momentum. They would outflow the GT40 heads while simultaneously maintaining better combustion chamber characteristics that improved efficiency and reduced the tendency toward detonation. Used E7TE truck heads cost about $40 a pair at any junkyard because nobody wanted them. A professional porting job ran about $400. You'd end up with heads that outperformed $1,200 GT40 heads in every measurable category. Ford knew this. They had the flow bench data because they built both parts on the same equipment. They had the combustion analysis because their engineers were thorough people doing their jobs properly. They chose to sell you expensive GT40 heads anyway because the product line demanded it. And the diesel world had their own revelations that were in some ways even more egregious because diesel trucks were working tools that people depended on for their livelihood. The turbocharger from a 1999 through 2003 Volkswagen TDI, a small European passenger car diesel designed for fuel efficiency and quick throttle response in urban driving, was perfectly sized for the 6.5-liter GM diesel trucks when modified appropriately for higher boost pressure applications. The stock GM turbo was laggy at low RPM, inefficient across most of its operating range at higher boost levels, and prone to bearing failures that left truck owners stranded with loads they couldn't afford to lose. The VW unit spooled faster due to its smaller turbine wheel, mapped more efficiently across the RPM range where working trucks actually spent most of their time, and was built by a manufacturer with a serious commitment to diesel durability because European diesel passenger cars had demanding customers who expected 200,000 miles without major failures. Mechanics were buying wrecked TDIs for their turbos, adapting them to GM diesels with fabricated exhaust housings and modified compressor outlets, and seeing 50 horsepower gains combined with better low RPM response and lower exhaust gas temperatures that extended engine life. A $200 Junkyard VW Turbo was outperforming GM's $1,000 factory unit in every category that mattered to someone using the truck as an actual tool. The technical reasons these swaps worked reveals something profound about automotive engineering that the industry prefers you not think about too carefully. Every component in every vehicle is a compromise between cost, performance, reliability, emissions requirements, and marketing positioning. But the compromise point chosen by the manufacturer is different for every application, and those different compromise points create opportunities for cross-pollination that the manufacturers never anticipated or wanted. A truck needs strong low-end torque for pulling loads from a standstill, so it gets heads with smaller ports that velocity the incoming air better at low RPM, building cylinder pressure before the piston reaches top dead center. A sports car needs high RPM breathing for track performance, so it gets larger ports that flow enough volume at high engine speeds to keep making power past 6,000 revolutions per minute. But what if you put those high-velocity truck heads on a performance engine and then spun it higher than the truck ever saw? Suddenly, you have the best characteristics of both applications combined in one package that neither manufacturer intentionally created. A diesel passenger car in Europe needs quick turbo spool and exceptional efficiency for fuel economy numbers that sell cars to cost-conscious buyers. A diesel truck in America needs durability above everything else because a catastrophic failure is a business liability, not just an inconvenience. But what if you take that efficient European turbo designed for quick response and reinforce the wastegate for higher boost pressure? Now you have efficiency and power from the same unit, a combination that neither manufacturer optimized for because neither was thinking about the other's application. The knowledge to understand this was always available. Detroit's engineers were smart people who understood these principles completely. The difference was that independent mechanics had zero reason to leave performance on the table and every incentive to find it wherever it was hiding. Let me explain exactly why the factories made these choices, using GM's own internal documentation. Using GM's powertrain division internal materials that surfaced during litigation proceedings in 2003, engineers operated under what they officially called deproliferation target. These were formal cost reduction goals expressed in the number of unique part numbers each vehicle line could use. Every unique part number cost money to inventory across the dealer network, costs to warranty separately, costs to service with dedicated tooling. So if a mediocre throttle body would technically function on 6 different engine applications, that's what got specified across all 6, even if a slightly larger unit would have meaningfully improved performance in 3 of those applications. The mediocrity was built into the system by design, justified with spreadsheets that nobody outside the company ever saw. There was also what engineers quietly called the step function problem in internal conversations. GM couldn't make the base Corvette perform too close to the Z06 because product planners needed clear performance separation to justify the price premium on the more expensive variant. They couldn't make the Z06 too close to the ZR1. They couldn't make the Camaro SS competitive with the Corvette at all. Each model needed distinct performance separation across the entire lineup, maintained through deliberate restriction of the less expensive variants even when $20 worth of improved components would have significantly closed the gap. The restrictions weren't engineering limitations. They were pricing strategy implemented through engineering decisions. Ford operated with identical philosophy, just with different product names and slightly different corporate language around the same fundamental decision-making process. The Mustang GT couldn't be performance competitive with the Cobra, which existed specifically to extract premium pricing from buyers who wanted more than the base model offered. The base F-150 couldn't threaten the Lightning's performance identity, which justified its own significant price premium. So Ford used restrictive airboxes specifically designed to limit airflow at high RPM, small throttle bodies that choked the engine when it most wanted to breathe, mild camshaft profiles that sacrificed top-end power for a smoother idle that focus groups preferred in clinic. Not because better parts didn't exist in Ford's engineering inventory. They were already sitting in Ford's parts bin, already being manufactured, already being installed in other vehicles where the product plan allowed their full potential to be realized. Ford just chose not to use them where they do the most visible good, because visible good created uncomfortable conversations about pricing and product positioning. But here's what most people don't realize about the geographic dimension of this restriction strategy. The same manufacturers were applying different standards to different markets simultaneously, which made the entire strategy visible to anyone willing to compare notes internationally. The Nissan SR20 DT sold in Japan produced 205 horsepower. The same engine configuration sold in European markets produced 200 horsepower. In America, they didn't even offer the turbocharged version initially, selling a naturally aspirated version rated at 140 horsepower while claiming the market wasn't ready for the performance variant. The blocks were identical castings. The heads came from the same tooling. The difference was the turbocharger system and the engine management calibration that Nissan chose not to ship across the Pacific, preserving the more powerful version for markets where enthusiasts were vocal enough to demand it. American mechanics started importing Japanese turbo manifolds and turbocharger assemblies, bolting them onto American SR20s that had been patiently waiting under econoboxes for someone to give them permission to perform. Perfect fitment, engineered to work together from the beginning because they came from the same engine family. Instant 205 horsepower from an engine that Nissan had been selling Americans in castrated form while simultaneously building the powerful version in the same factory. The Honda B16 told a nearly identical story. Japan received 170 horsepower. Europe received 160 horsepower. America received 160 horsepower, but with different camshaft profiles specifically selected to reduce top-end power delivery compared to the European version. Swap in Japanese camshafts. a job that takes about 20 minutes with basic tools and moderate mechanical confidence, and gain 10 horsepower with improved throttle response above 6,000 revolutions per minute. The cam profiles weren't dramatically different in specification. Just enough to meet some arbitrary decision someone made in a product planning meeting about power delivery characteristics in different markets. This is where it gets really interesting from a historical perspective, because these weren't isolated examples of one manufacturer making one questionable decision. This was systematic, industry-wide, coordinated suppression of available performance across every manufacturer operating in the American market during the regulatory environment that followed the 1973 emissions standard. The BMW M3 sold in America had 240 horsepower. The European version of the same car with the same S14 engine had 286 horsepower. The differences were an intake manifold designed for better high RPM breathing, an ECU calibration that allowed more aggressive timing advance across the operating range, and exhaust headers with better scavenging characteristics. American mechanics started sourcing European specification parts through gray market channels and discovering that they were bolt-on installations because BMW built one engine, then deliberately detuned specific components for the American version. BMW's official explanation involved emissions compliance, but the European cars met European emissions standards that were in many categories stricter than American standards during that period. The real reason was more straightforward and less defensible. BMW didn't want the M3 to generate insurance rate increases that would make it unaffordable for the demographic they were targeting. They didn't want dealer service departments dealing with customers who'd push these engines to their limits on track days. They didn't want the liability exposure that came with selling 286 horsepower to an American market they perceived as litigious and less track experienced than their European customer base. So they sold 240 horsepower and kept 46 horsepower in reserve, waiting for enthusiasts to figure out what had been taken from them. By the late 1990s, entire communities had formed around these discoveries, organized through early internet forums that connected mechanics across geographic barriers that had previously kept this knowledge fragmented and local. Forums dedicated to interchange guides, mechanics sharing flow bench data on heads from completely different manufacturers tested on the same equipment, dyno sheets proving in documented, repeatable fashion that a $75 junkyard part outperformed $1,000 aftermarket pieces that had professional marketing budgets and glossy catalog photography. The automakers took notice of these communities, and their response revealed exactly how threatened they felt by the democratization of performance knowledge. Technical service bulletins started appearing at dealer service departments specifically warning that using non-approved interchange parts would void warranty coverage, even on engines that were already years out of their original warranty period and being maintained by enthusiasts who had no warranty to void anyway. Some manufacturers changed part designs specifically to prevent interchange that had been documented as working effectively. GM redesigned bolt patterns on newer throttle body applications to prevent the easy swaps that mechanics had been doing for a decade. Ford changed the fin pitch and end tank designs on their intercoolers so that proven older units wouldn't physically fit newer applications without significant additional fabrication work. These were not engineering improvements. They were deliberate countermeasures against people who were outsmarting the product plan. It was admission by action that the swaps worked, and the manufacturers wanted to stop them. But it was far too late to contain knowledge that had already been documented, shared, and proven across thousands of builds in every state. The second generation of mechanics who grew up reading these forums took the accumulated knowledge even further than the pioneers who discovered it. They began combining multiple junkyard insights into coherent build philosophies that completely transformed engines without a single aftermarket component. The junkyard jewel movement formalized this approach with a specific challenge: build a 500 horsepower small block Chevrolet using only factory original equipment manufacturer parts sourced from production vehicles. No aftermarket components except gaskets, fasteners, and fluids. Everything else had to come from an application where some manufacturer had installed it as original equipment. Here's what one documented build actually looked like, with dyno sheets that exist in forum archives to this day. Start with a 1996 Chevrolet Truck 350 block, specifically the last model year, with a one-piece rear main seal that simplified assembly, while still having provisions for a mechanical fuel pump that kept the fuel system simple and reliable. Add a forged crankshaft from a 1970 LT1 engine found in a wrecked Corvette that had accumulated enough miles to be considered totaled but still had a perfectly rebuildable bottom end. Eagle SAR connecting rods from a 1995 Caprice Police Interceptor, forged units that GM installed specifically because police fleets demanded durability that could survive pursuit driving conditions that consumer vehicles never saw. Pistons from a Marine 383 application, forged units dished for lower compression ratio, perfect for the forced induction application being planned. Cylinder heads came from those adapted 454 truck units documented earlier in this movement's history, the ones that flowed 44% better than stock small block heads while using the high-velocity port design that built excellent cylinder pressure across a broad RPM range. The camshaft was the hydraulic roller profile from a 1996 Vortec truck engine, which had more lift and more duration than anything GM specified for a passenger car application because truck engineers needed torque and durability rather than smooth idle quality for marketing demonstrations. Intake manifold was the long runner design from a 1993 LT1, modified to work with conventional pushrod heads using a fabricated adapter that cost about $50 in materials and an afternoon of careful machine work. The throttle body was that 52mm unit from the Impala SS we discussed earlier, the one GM had been installing on full-size sedans while starving the Camaro of airflow for product positioning reasons. 4 forced induction, a turbocharger from a 2003 Volvo V70, perfectly sized for a 350 cubic inch engine in terms of compressor map coverage, incredibly efficient in the mid-boost range where streetable builds spend most of their time, and built by Mitsubishi's commercial division to survive 200,000 miles in a Swedish family wagon that operated year-round in conditions that would destroy lesser hardware. Intercooler from a Thunderbird Super Coupe, the original discovery that started this entire movement. Wastegate actuator from a Saab 9000, noted for its precision and reliability across wide temperature ranges. Oil cooler from an Isuzu NPR commercial truck, overbuilt for continuous heavy-duty operation in exactly the thermal conditions that a boosted performance engine create. Total investment under $2,000. Assuming the builder performed their own assembly work and sourced parts patiently rather than paying junkyard premium pricing. Power output on the dyno was 515 horsepower at 12 pounds of boost, with a torque curve that was flat and usable from 2,800 revolutions per minute all the way to the 6,200 revolutions per minute redline. Completely streetable with proper fuel management, emissions legal in most states with appropriate tuning, and built using zero aftermarket performance parts marketed to enthusiasts at enthusiast pricing. The same engine built exclusively with cataloged aftermarket components from recognized performance brands would have cost between $8,000 and $10,000 to assemble to the same power level. The Junkyard build proved that Detroit had been capable of building 515 horsepower engines all along. They had every single part required sitting in their production inventory, installed in separate vehicles, kept deliberately separated by brand loyalty and market segmentation that the manufacturers cultivated and maintained at significant marketing expense. The modern evolution of this movement became even more sophisticated once affordable wideband oxygen sensors and tunable engine management systems became accessible to independent builders in the early 2000s. Where earlier mechanics had to rely on empirical observation and educated mechanical intuition to optimize their combinations, now they could watch exactly what the engine was doing in real time and make calibration changes that extracted every available unit of performance from the combination while protecting the engine from conditions that would shorten its life. They discovered that the knock sensors from a Nissan 300ZX were significantly more sensitive to early detonation events than the knock sensors GM had been using, and would bolt directly into the same sensor bosses that GM had machined into their blocks for decades. Better knock detection capability meant more aggressive baseline timing advance, more power everywhere in the RPM range, and simultaneously better protection because the system caught problems earlier in their development. The cam position sensor from a Jeep 4.0-liter inline-six was more dimensionally accurate in its reluctor-wheel relationship than Ford's equivalent sensor from the same era, and could be adapted with minor wiring harness modifications to work with Ford engine management systems. More accurate camshaft position information meant better injection timing, better ignition timing relative to valve events, better emissions, and better drivability across the operating range. The mass airflow sensor from a 2003 through 2004 Ford Mustang Cobra became the universal recommendation for any build targeting over 400 horsepower. Ford had finally sized this component properly, probably because the Cobra's power level demanded it rather than because of any deliberate generosity toward the enthusiast community. It would read airflow accurately up to approximately 700 horsepower before saturating its measurement range. Junkyard Cobras were being purchased specifically for their mass airflow sensor housings, while the rest of the car provided additional useful components for other projects. The electronic throttle body from a 2005 Corvette became the definitive choice in the LS engine swap community that was reshaping how performance builds were approached across every vehicle platform. 90mm bore diameter, integrated idle air control that eliminated the need for a separate component, an electronic motor assembly that proved essentially bulletproof in thousands of applications. GM listed it at $500 through their parts counter. Junkyard examples from wrecked Corvettes sold for around $100, representing exactly the same part with exactly the same performance capability at 80% cost reduction. The principle that drove the entire junkyard engineering movement was still working perfectly decades after Mike Lurski's first intercooler swap. But here's what truly exposed the depth of Detroit's deliberate limitation strategy in a way that left no room for alternative interpretation. When independent mechanics began posting their results online with documented dyno sheets, verified track timing slips, and detailed build lists that any reader could replicate, the manufacturers began releasing special edition vehicles and performance upgrades that incorporated the exact modifications the junkyard movement had been documenting for years. GM suddenly discovered that larger throttle bodies meaningfully improved performance and released the ZL1 Camaro with a 90mm unit that closely resembled what mechanics had been adapting from truck applications for a decade. Ford realized that proper intercooler sizing made significant measurable power, and the new generation Raptor received a massive intercooler core that looked remarkably similar in design philosophy to what mechanics had been adapting from diesel truck applications. Chrysler announced crate engines with improved cylinder heads that flowed in ranges suspiciously similar to what mechanics had been achieving through careful porting of truck castings. They knew all along. The capability was never absent from their engineering departments. The knowledge was never missing from their design files. The parts were always sitting in their production inventory, installed in trucks and commercial vehicles and international variants that American performance buyers weren't supposed to connect to their sports cars and muscle cars. The decision to withhold was deliberate, financially motivated, and sustained across decades of production. Every time an enthusiast bought an aftermarket performance part at premium pricing when an equivalent factory component was sitting in a junkyard 20 minutes away, the system worked exactly as intended. The economics of this deliberate restriction are genuinely staggering when you calculate them across actual production volumes rather than looking at individual vehicles. The Ford Mustang GT produced from 1987 through 1993 was rated at 225 horsepower. With documented junkyard modifications, E7TE truck heads properly ported by a competent machine shop, Explorer intake manifold, 65mm throttle body from a Lightning, headers from a truck application, that same engine reliably produced 300 horsepower. Ford sold approximately 450,000 Mustang GTs during those model years. Including these improvements in factory production would have added perhaps $200 per car in manufacturing cost, totaling roughly $90 million across the production run. But a 300 horsepower Mustang GT could have commanded $1,000 more in showroom pricing, representing $450 million in additional revenue against a $90 million investment. The margin improvement would have been dramatic. But then the Mustang GT would have been directly competitive with the Thunderbird Super Coupe, which existed at a higher price point and needed clear performance separation to justify that premium. It would have uncomfortably approached Corvette performance territory, and the Corvette was GM's flagship that Ford certainly didn't want to destabilize by making their mass-market pony car too capable. Insurance companies would have increased rates on Mustangs already near the threshold where coverage costs deterred younger buyers who were the primary demographic. The entire carefully constructed ecosystem of performance tiers, brand differentiation, and market segmentation would have been destabilized by one honest engineering decision on one model. So instead, they sold 225 horsepower Mustangs to loyal customers and distributed the additional 75 horsepower worth of components across their trucks, vans, and specialty applications, trusting that brand loyalty and mechanical ignorance would keep enthusiasts from connecting the dots. The story of Mike Lurski has an ending that captures this entire history in a single anecdote. His junkyard intercooler swap on that original Grand National became so thoroughly documented and widely known within the Buick performance community that he started a business performing the conversion professionally. He sourced every Thunderbird Super Coupe intercooler he could locate through junkyard contacts across 3 states, developed a refined fabrication process that made each installation cleaner and more reliable than the previous one, and sold complete swap kits with detailed instructions to mechanics who wanted to do the work themselves. General Motors could have responded with legal challenges about intellectual property or warranty interference. Instead, they hired him as a consultant to help develop the intercooler system architecture for their upcoming turbocharged Ecotec engine family. The modifications they had avoided for cost reasons across 30,000 Grand Nationals, they now wanted his practical expertise to implement on millions of future vehicles. The junkyard engineer teaching Detroit engineers what they had always pretended not to know, because finally the product plan allowed them to apply it. What's the most unexpected junkyard swap you've ever seen actually work on the dyno? Drop it in the comments below and share your knowledge with everyone watching, because that's exactly how this movement has always stayed alive. Not through corporate permission or manufacturer blessing, but through shared discovery between mechanics who cared more about making things work than maintaining anyone's brand loyalty. Keep turning wrenches, keep questioning why things are the way they are, and keep looking at every car in every junkyard as a collection of engineering solutions waiting for someone creative enough to see what they could become in a different application. Because somewhere in that sea of discarded metal is the exact part that solves your specific problem better than the factory ever intended to allow. You just have to know where to look. 8,500 revolutions per minute. That's the number that broke every rule anyone in racing thought they knew. And here's the thing, it didn't come from a factory lab, a $1 million R&D budget, or some team of aerospace engineers hunched over computers. It came from one guy in Ohio who refused to accept that the way everyone else was doing it was actually the right way. Bill Jenkins didn't just bend the rules of drag racing. He looked at a transmission that General Motors designed for suburban housewives hauling groceries, and he turned it into the most dominant piece of racing equipment in pro stock history. And the wildest part? The engineers who built that transmission never saw it coming. This is automotive ancestry, and I spend way too much time thinking about the mechanical decisions that quietly rewrote the rulebooks of motorsports history. If you're someone who loves digging into the engineering stories behind iconic racing breakthroughs and wants to understand not just what happened on the track but exactly why it happened under the hood, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, before we get into the specifics of what Jenkins actually did, I want to paint you a picture. Because understanding this story isn't just about transmission specs and gear ratios. It's about what happens when one person's willingness to think differently collides with an entire sport's worth of accepted wisdom. And when that collision happens, sometimes the sport never looks the same again. Picture this. It's a humid Saturday night at National Trail Raceway outside Columbus, Ohio. The kind of night where the air is so thick with tire smoke and racing fuel that you can almost taste it. In the staging lanes, million-dollar race teams are making final adjustments to their pro stock machines. And look, these aren't street cars with racing stripes and hood scoops bolted on for show. These are purpose-built quarter-mile weapons producing north of 800 horsepower from naturally aspirated small block. Every component has been massaged, machined, and modified to within an inch of its life. These teams have the best parts, the best tires, the best crew chief's money can buy. Yet when the Christmas tree drops and these mechanical monsters launch down the track, one Vega keeps pulling away. Not because it has more power, not because it's lighter, but because its transmission is doing something that, according to everything anyone knew at the time, flat out shouldn't be possible. That Vega belonged to Bill Jenkins. And the thing doing the impossible inside it was a transmission Chevrolet introduced in 1950 as a simple, reliable automatic for everyday drivers who just wanted to forget shifting existed altogether. Now, you might be thinking, wait, a two-speed automatic from 1950 beating purpose-built race cars in the mid-1970s? That sounds like someone got their facts mixed up. But stick with me here, because this is where it gets really interesting, and the engineering logic behind it is something that, once you understand it, you will never look at a gear shift the same way again. Bill Jenkins wasn't just another weekend warrior with a fast car and a dream. This was Grumpy Jenkins, a man who had already revolutionized pro stock racing with a scientific approach to engine development that was genuinely ahead of its time. While other racers relied on gut feelings, old-timer wisdom passed down through the pits, and the collective memory of what worked last season, Jenkins approached drag racing the way a physicist approaches particle acceleration. He had notebooks filled with equations. He had dyno charts wallpapering his shop. He had a mind that could calculate gear ratios, power curves, and elapsed times faster than most people could read them off a timing slip. But his greatest innovation, the one that actually changed the sport forever, wasn't in the engine compartment at all. It was in that transmission. The humble, allegedly grocery-getter Power Glide. Here's what most people don't realize about the Power Glide. Its simplicity wasn't a weakness. It was a blank canvas. While other manufacturers in the early 1950s were developing sophisticated multi-speed automatics with elaborate valve bodies and complicated hydraulic circuits that required specialist knowledge just to diagnose, Chevrolet took a completely different path. 2 forward gears, low and high, a torque converter, a simple planetary gear set, a few clutches and bands. That's basically it. Nothing fancy, nothing exotic, nothing that required a degree to understand. Just clean, simple mechanical logic. And here's the thing about simple designs. They're easier to understand completely. And when you understand something completely, you can push it to places its creators never imagined. You can see the limits not as walls but as starting lines. The conventional wisdom in 1975 was clear: established, and agreed upon by virtually every experienced racer, crew chief, and magazine writer in the sport. You shifted when the engine started falling off its power peak. For a built small block, that meant somewhere around 6,500 revolutions per minute. You hit that number, you shifted, you let the next gear take over and get back into the power band. Every racing manual said it. Every experienced voice in the paddock confirmed it. It was gospel. Jenkins thought the gospel might be wrong. He had spent hundreds of hours on the engine dyno, not just measuring peak power like most builders, but studying in precise detail exactly how power behaved after peak. What he found was something subtle but explosive in its implications. Yes, power dropped after peak RPM. But it didn't fall off a cliff. A properly built race engine might make 820 horsepower at 7,200 revolutions per minute, then 780 horsepower at 8,500 revolutions per minute. That's a 40 horsepower loss. On paper, that sounds like a reason to shift earlier. But Jenkins did the math that everyone else was too busy or too comfortable to do. And the math told a completely different story. When you shift from first to second in a power glide, your engine RPM drops dramatically because the gear ratio changes hard from 1.76 to 1 down to 1.0 to 1. If you shift at 6,500 revolutions per minute following conventional wisdom, your engine drops to roughly 3,700 revolutions per minute in second gear. Now you're way below peak power, maybe making 550 horsepower, crawling back up the power curve while your competitor is already further down the track. But if you hold first gear all the way to 8,500 revolutions per minute, even though you're past peak power in that gear, you shift into second at around 4,800 revolutions per minute. You're making closer to 700 horsepower immediately after the shift. That's 150 more horsepower working for you right out of the gate in second gear. Jenkins understood something fundamental that the rest of the racing world had missed entirely. Drag racing isn't about peak power. It's about average power across the entire run. Every millisecond you spend below peak power is a gift to your competitor. By shifting at what seemed like a dangerously high RPM, Jenkins kept his average power higher throughout the quarter mile. It was not a guess. It was not intuition. It was math. Cold, precise, unambiguous math. But understanding the theory was only half the battle. The power glide was not designed to shift at 8,500 revolutions per minute. It wasn't designed to even see 8,500 revolutions per minute. Making it work required essentially reimagining the transmission from the ground up while keeping its fundamental simplicity intact. Jenkins started with the valve body, the hydraulic brain of the transmission. The factory valve body used precisely sized passages and calibrated spring pressures to determine shift behavior, all tuned for smooth, comfortable operation at street speeds. Jenkins machined new passages, increasing their diameter to flow more fluid more quickly. He installed stiffer springs that required higher hydraulic pressure to compress, effectively raising the ceiling on where the transmission would agree to shift. This wasn't just drilling bigger holes. It was a calculated recalibration of an entire hydraulic system. The clutch packs were next. Factory Power Glide clutches were designed for 100,000 miles of gentle suburban use. Organic friction materials, smooth engagement, long service life. Jenkins replaced them with sintered metallic clutches, the same technology used in aircraft braking systems. These could handle temperatures that would literally vaporize stock materials. They engaged harder, faster, and could absorb the punishment of repeated high RPM shifts without glazing, burning, or fading. Line pressure was cranked from a factory 90 psi up to 200 psi. This required a modified pump, stronger pressure regulator springs, and reinforced case passages. Higher pressure meant faster and firmer shifts, but it also meant every seal, every gasket, and every bearing was living beyond its original design limit. The difference between what Jenkins built and what a lesser builder would have created with the same modifications is the difference between a precision instrument and a bomb. The torque converter required complete rethinking. Stock converters were engineered for smooth coupling across a broad RPM range. Jenkins needed a converter that would flash to high RPM instantly and then couple efficiently without slippage bleeding away the power he was working so hard to preserve. He worked with specialized converter builders to develop custom units with modified stator angles, different fin configurations, and precisely calibrated internal clearances. These converters were so specialized they were nearly useless in any street application, but on the track they were perfect partners for the engine and transmission combination he was building. Testing is where Jenkins truly separated himself from everyone else attempting similar modifications. He didn't bolt in his modified transmission and take it to the track on faith. He had a transmission dyno in his shop, a piece of equipment most race teams never considered necessary. Every modification was tested, measured, and documented before it ever saw a race. He could measure shift timing down to milliseconds, record hydraulic pressure traces during shifts, and monitor temperatures at multiple locations throughout the unit. When something failed during development, and failures happened constantly, he knew precisely why, precisely where, and precisely what to change next. Now, when Jenkins first showed up at a race running his high RPM power glide strategy, the reaction from the paddock was exactly what you'd expect: confusion, then skepticism, then something close to pity. Veteran racers heard his engine screaming past what sounded like any reasonable shift point, still pulling in first gear while they were already in second and working toward peak power again. They shook their heads. They told each other he'd grenade the transmission before the run was over. They waited for the aluminum confetti and puddle of fluid. But the timing slips kept coming back with lower numbers. Run after run. Event after event. Jenkins Vega kept winning. Not squeaking by, not catching lucky break. Winning consistently by meaningful margins against teams with bigger budgets, more sophisticated equipment, and decades of accumulated racing wisdom on their side. The first response from the racing community was denial. He must have a bigger engine. Hidden nitrous. Some trick buried deep in the motor that the rulebook doesn't allow. Tech inspectors pulled his car apart after wins and found nothing but a legal small block and that weird, ancient two-speed automatic. Then came the rationalizations: better traction, lucky lane conditions, statistical variance. But as wins piled up and excuses wore thin, the community moved to the only rational conclusion left. Jenkins had found something real. What followed was imitation on a massive scale. Within 6 months, every serious pro stock team was experimenting with high RPM shift points. Transmission builders who had been in business for decades suddenly had to fundamentally relearn their craft. Parts manufacturers scrambled to develop components capable of surviving the new demand. An entire industry rewrote its understanding of what a power glide was for. Here's what most people don't realize about that period. Most teams could copy what Jenkins did mechanically, but they couldn't replicate his result. They had the same shift point numbers, similar modifications, comparable parts. But they didn't have the complete picture. Because Jenkins understood that the high RPM power glide was just one part of an interconnected system, and every other part of that system had to be rebuilt around the same philosophy. The engine had to genuinely survive and continue making power at speeds it was never originally designed to see. That meant stronger valve springs, titanium valves, better rod bolts, rotating assemblies balanced to tolerances that would have seemed excessive to most builders. The cooling system needed upgrading because sustained high RPM operation generates dramatically more heat than the factory engineers ever planned for. The oiling system required modification to maintain pressure and adequate flow at speeds where oil starvation becomes a real and immediate threat. The camshaft profile was crucial in a way that most people copying Jenkins missed entirely. Standard race cams of that era were designed for peak power in the 6,000 to 7,000 RPM range. Jenkins worked directly with cam grinders to develop profiles that would carry power effectively out to 8,500 revolutions per minute without valve float destroying the power curve or the valve train itself. These cams had more lift, longer duration, and steeper ramps than anything else being run competitively. They made the engine essentially undrivable below 3,000 revolutions per minute. But Jenkins wasn't building something that needed to be pleasant on the street. He was building a system optimized entirely for one thing. Valve springs became their own engineering project. At 8,500 revolutions per minute, valves are opening and closing 71 times per second. Springs have to be strong enough to control the valves at those speeds but calibrated carefully enough that they don't accelerate where on cam lobes or risk breaking valve stems. Jenkins tested dozens of combinations, measuring installed height, seat pressure, and open pressure with the kind of meticulous documentation that most racers reserved for engine specs alone. He found that dual springs with dampers outperformed singles consistently, and that spring temperature during operation was as important a variable as spring rate. Details like that don't come from guessing. They come from hundreds of hours of disciplined testing. The bottom end needed to be genuinely bulletproof. Stock connecting rods would fail catastrophically at 8,500 revolutions per minute under race load. Jenkins used aftermarket forged steel rods, shot-peened for stress relief and sized to exact tolerances. Custom forged aluminum pistons, designed specifically for the increased cylinder pressures and temperatures his engine would see. The crankshaft was a masterpiece on its own, knife-edged for reduced windage, cross-drilled for better oiling distribution, balanced to a standard of precision that reflected Jenkins's obsession with getting every detail right. But perhaps the most impressive aspect of Jenkins's complete approach was his understanding of vehicle dynamics as a total system rather than a collection of individual components. He realized that keeping the engine in its power band throughout a quarter-mile run wasn't just about the transmission shift point. It was about the relationship between that shift point, the rear axle gear ratio, the tire diameter under load, and even the aerodynamic drag at speed. He calculated exactly what rear gear ratio would optimize the relationship between engine RPM and vehicle speed given his new shift point strategy. He chose tire sizes and compounds that would grow predictably under acceleration, effectively changing the final drive ratio in a controlled way as speed increased. He even addressed aerodynamic drag at the speeds where his high RPM advantage was most significant. The data acquisition Jenkins used was primitive by today's standards but genuinely revolutionary for 1975. Strain gauges on the driveshaft to measure torque delivery. Pressure transducers inside the transmission to monitor shift quality and hydraulic behavior. Thermocouples positioned throughout the drivetrain to track temperatures at critical points. Everything recorded on paper charts that Jenkins would study for hours after each race session while other racers were socializing in the paddock. This was the part of the work that never made it into the magazine stories, but made everything else possible. Chevrolet's official position was predictably careful. Operating the Powerglide beyond design specifications voided the warranty and was not recommended under any circumstances. But unofficially, the company's engineers were fascinated. Several Chevrolet engineers made visits to Jenkins's shop under the cover of routine technical support, but their real interest was in understanding what he had discovered about their own transmission's capabilities. The knowledge that flowed from that relationship would eventually influence the design philosophy behind future performance transmissions in ways that the company never formally acknowledged. The safety implications of what Jenkins pioneered were serious and immediate. An 8,500 revolutions per minute transmission failure isn't just expensive. It's genuinely dangerous. The energy stored in rotating components at those speeds is enormous, and when catastrophic failures occurred, the results were dramatic. transmissions that would physically cut through floorboard, explosions that could lift the front of a car off the ground. Drivers required additional protection, including ballistic blankets wrapped around the transmission tunnel and reinforced firewall construction. Jenkins himself developed strict maintenance schedules that seemed obsessive from the outside but were essential for safety and consistency. Complete teardown and inspection every 20 runs. Clutch pack replacement every 50. Valve body cleaning and recalibration every 10. The cost in parts and labor was staggering, but for teams competing at the highest level of pro stock, it was simply the price of operating at the frontier. The psychological dimension of what Jenkins created is something that rarely gets discussed, but it was real and it mattered. When competitors in the staging lanes heard his engine screaming past 8,000 revolutions per minute and still pulling hard in first gear while they were already in second, it was demoralizing in a way that went beyond simple intimidation. They understood, in that moment, that something fundamental had changed about the game they were playing. Some teams attempted to match his RPM strategy without understanding the complete engineering package behind it, resulting in spectacular failures that cost them equipment and further cemented Jenkins's reputation as someone operating on a genuinely different intellectual level than the rest of the field. This is where it gets really interesting in terms of broader impact. The lessons Jenkins demonstrated at National Trail Raceway and dozens of other tracks across the country rippled outward far beyond pro stock drag racing. Road racers began examining their shift point assumptions with fresh skepticism. NASCAR teams started running data-driven experiments on holding gears longer in specific track situations. The fundamental principle that average power across a run matters more than peak power at any given moment is so obvious once stated that it seems impossible it needed proving. Yet it did need proving, and Jenkins proved it. The evolution of what Jenkins started continued through the late 1970s and into the 1980s at a pace that would have seemed impossible just years earlier. As engines became more powerful and better understood, transmission technology had to keep pace or become the limiting factor. Jenkins pioneered the use of trans-brake systems, which allowed drivers to load the torque converter against a held transmission for dramatically more violent and consistent launches. He experimented systematically with different fluid formulations, finding that early synthetic fluids could handle higher operating temperatures while maintaining more consistent viscosity and shift behavior than conventional petroleum-based alternative. He developed custom shifter mechanisms capable of initiating shifts faster than any human driver could manage through direct input. The aftermarket that grew around Jenkins's innovations became an industry in its own right. Shops specializing in high-performance power glide preparation appeared across the country. Parts manufacturers developed entire product lines specifically for these applications. Torque converter builders who had previously focused on street performance applications retooled their businesses around the demands of high RPM racing. Jenkins had, through the simple act of questioning one assumption about shift points, created an entire ecosystem of specialized knowledge and commerce. Here's what makes the Jenkins story resonate beyond motorsports, beyond mechanical engineering, and honestly beyond anything specifically automotive. It's a story about what actually happens when someone refuses to accept that established rules are correct simply because they're established. And look, this isn't some motivational poster concept. This is a concrete, documented, measurable case study in what questioning assumptions actually looks like in practice. Jenkins didn't walk into the paddock and announce that everyone was wrong. He went back to his shop, ran his numbers, tested his theories, documented his results, and let the timing slips make the argument for him. Now, you might be thinking that this kind of innovation is unique to someone like Jenkins, a genuine genius with an unusual mind and an unusual level of obsession. And fair enough, there's something to that. But here's what most people don't realize about how Jenkins actually got to his insight. It wasn't a single lightning bolt moment. It was an accumulation of small observations, each one building on the last, over years of careful work. The 8,500 revolutions per minute shift point wasn't a guess that happened to pay off. It was the conclusion of a methodical process that started with a simple question: what if the conventional shift point isn't actually optimal? That question sounds simple, but asking it sincerely, following it honestly wherever the data leads, and then being willing to look strange in front of an entire paddock full of experienced people who think you've lost your mind, that's harder than it sounds. Most people, confronted with universal consensus, find a way to convince themselves that the consensus is probably right and move on. Jenkins didn't. And that difference, that specific refusal to defer to collective wisdom without evidence, is what separated him from equally talented, equally experienced competitors who had access to the same basic equipment and the same basic information. The Power Glide itself deserves more direct attention here because it's genuinely fascinating as an engineering artifact. When Chevrolet introduced it in 1950, the transmission market was developing rapidly and in multiple directions simultaneously. Other manufacturers were chasing complexity, adding speeds, adding sophistication, adding features that made their transmissions feel modern and progressive. Chevrolet's engineers made a choice that looked conservative at the time and turned out to be visionary in ways they never anticipated. They optimized for reliability and simplicity over sophistication. They built something that a reasonably skilled mechanic could completely understand, completely disassemble, and completely rebuild without specialized factory tooling or exotic knowledge. That design philosophy created the conditions that made Jenkins's innovation possible. A more complex transmission, even a more capable one in factory form, would have been far harder to modify with precision. The number of interacting variables would have multiplied, making it much more difficult to isolate the effect of any specific change. The Power Glide's simplicity made it a perfect experimental platform precisely because there wasn't much in it to confuse the result. When Jenkins changed the valve body, he knew what he'd changed and could measure the specific effect. When he modified the clutch packs, the result was traceable and documentable. Complexity, in this case, would have been the enemy of innovation. There's a broader lesson here that applies to engineering philosophy in general and gets missed in the modern conversation about performance technology. We tend to assume that more sophisticated always means more capable of improvement, but sophistication creates interdependencies that can actually limit the ceiling of what's achievable. The Power Glide had a higher ceiling for specific modifications than more complex transmissions of its era precisely because its simplicity meant that individual elements could be pushed harder without cascading negative effects throughout the system. Jenkins was smart enough to recognize that advantage and exploit it fully. The cam development work that Jenkins undertook in parallel with his transmission modifications is worth examining in some detail because it illustrates how completely he understood the system he was building. Working with cam grinders to develop profiles that would sustain power out to 8,500 revolutions per minute required understanding not just the power curve but the physics of valve motion at those speeds. Valve train dynamics become genuinely difficult to manage as RPM climbs. The mass of the valve, spring, retainer, and associated components creates inertia that the spring has to overcome on every single cycle. At 8,500 revolutions per minute, you have almost no time to manage that inertia between cycles. If the spring isn't strong enough, the valve doesn't close fully and you lose compression and power. If it's too strong, it accelerates where at contact points and can cause other failures. Jenkins worked through these problems iteratively, which is to say he tested, failed, analyzed, adjusted, and tested again. This is not a glamorous process. It doesn't make for exciting magazine coverage, but it is the actual process by which genuine engineering advancement happens. The breakthroughs that make it into the history books are usually the visible peaks of enormous invisible mountains of quiet, careful, repetitive work that nobody outside the shop ever sees. The relationship between Jenkins and the engine builders he worked with is another dimension of this story that deserves recognition. He wasn't operating in isolation. He was the center of a network of specialists, each of whom contributed expertise in their specific area. Converter builders who understood fluid dynamics, cam grinders who understood valve train physics, machine shops that could hold tolerances tighter than their equipment was rated for because the machinist understood why it mattered. Jenkins's genius wasn't just technical, it was organizational. He knew how to identify the right people, communicate what he needed with precision, and integrate their contributions into a coherent whole. This is where it gets really interesting when you think about what Jenkins accomplished in a competitive context. He was, at various points in the mid-1970s, simultaneously ahead of the entire pro-stock field in transmission development, engine development, and vehicle dynamics understanding. Any one of those advantages alone might have produced some wins. All three working together in an optimized system produced dominance. His competitors could copy individual elements but couldn't replicate the integration because they didn't have a complete model of how the elements interacted. They had pieces of the picture. Jenkins had the whole thing. The data acquisition system Jenkins developed deserves more credit than it typically receives in retrospective coverage of this period. Look, by modern standards, strain gauges and thermocouples recorded on paper charts seem laughably primitive. Today's pro-stock teams run sophisticated telemetry systems that collect thousands of data points per second and process them in real time. But the principle Jenkins was applying, measure everything, record everything, analyze systematically, act on evidence rather than intuition, is identical to the principle behind modern data-driven racing. He was practicing data-driven development in 1975 with 1975 tools, which is to say he was practicing it decades before the culture of motorsports broadly accepted that this was how serious development work needed to happen. The maintenance regime Jenkins imposed on his transmission program also reflects a sophistication that was well ahead of its time. The schedule of teardown and inspection every 20 runs, clutch replacement every 50, valve body service every 10, looks like conservative overcaution until you understand what he was actually doing. He was managing the degradation of components that were operating beyond their designed limits as a controlled process rather than waiting for random failures. By inspecting on a schedule driven by his test data rather than by manufacturer recommendations designed for street use, he could catch developing problems before they became catastrophic failures. He was trading the cost of preventive maintenance for the far larger cost of unexpected failures at race events. That trade makes obvious sense stated plainly, but it required the discipline to actually execute it consistently and the data foundation to set the intervals intelligently. By the late 1970s, the innovations Jenkins had pioneered had spread through pro-stock racing so completely that they were no longer innovations. They were simply the baseline. Teams that weren't running high RPM shift strategies were at a structural disadvantage that no amount of power or money could overcome. The Power Glide had gone from grocery getter transmission to the only viable choice for serious pro-stock competition. Builders who had spent careers mastering other transmissions had to either learn the Power Glide from scratch or exit the market. New specialists who had grown up learning the Power Glide in its modified form became the most sought-after transmission builders in the sport. The irony that sits at the center of this entire story is worth sitting with for a moment. General Motors introduced the Power Glide because they wanted a transmission simple enough that drivers could forget about shifting altogether. The transmission designed specifically to remove the driver from the shifting equation became, in Jenkins's hands, the precision instrument that required the most sophisticated shifting strategy in the sport. The engineers who designed it for maximum user simplicity created something that would eventually demand maximum engineering sophistication to exploit. They couldn't have predicted it, but they created the conditions for it. Here's the thing about truly foundational innovations. They tend to generate consequences that extend far beyond the immediate context in which they appear. Jenkins's work on the Power Glide wasn't just about winning pro stock races. It was a proof of concept for a way of thinking about performance development that influenced how serious teams across multiple forms of motorsports approach their work. The questions he modeled: what does the data actually show? What assumption is everyone making that might be wrong? How does this component interact with every other component in the system? Are questions that define serious engineering development in any context. The conversation around Jenkins's legacy often focuses, understandably, on the dramatic element. One man, one weird idea, an entire sport forced to change its understanding. It's a compelling narrative because it's true, and because the human instinct for stories of individual genius against collective wisdom is powerful. But focusing exclusively on the drama risks missing the deeper lesson that makes this story genuinely useful rather than simply entertaining. Jenkins didn't succeed because he had a flash of insight that nobody else could have had. He succeeded because he built a rigorous process for testing ideas that most people wouldn't have bothered to test. The insight that average power matters more than peak power is, stated plainly, not a difficult concept to grasp. It follows logically from basic physics. A physicist looking at drag racing for the first time, without any of the sport's accumulated conventional wisdom, might arrive at the same conclusion in an afternoon. The remarkable thing isn't that Jenkins had the idea. The remarkable thing is that he was the one person in an entire sport full of intelligent, experienced people who actually followed the idea all the way through to its physical implementation. This points to something important about how conventional wisdom actually functions within any specialized community. It's not maintained because people are stupid or lazy, though those factors sometimes apply. It's maintained because it works well enough that questioning it carries a real cost with no guaranteed payoff. Shifting at 6,500 revolutions per minute was a winning strategy for most of the field most of the time. It was good enough, and good enough is the enemy of better, not because better is impossible, but because good enough removes the urgent motivation to find it. Jenkins's motivation to find something better came partly from competitive pressure and partly from a genuine intellectual restlessness that refused to accept good enough as a destination. Here's what most people don't realize about the transmission development work happening during this period across the broader racing world. Multiple teams and builders were simultaneously pushing in various directions, experimenting with different approaches to extracting more performance from available transmissions. Jenkins wasn't operating in a vacuum of innovation. What distinguished his results wasn't that he was the only person experimenting. It was that he was the most systematic about it, the most honest in his analysis of results, and the most willing to follow evidence into uncomfortable territory. Other builders were doing experiments. Jenkins was doing science. The difference in outcomes reflects the difference between those two activities. The clutch pack development work represents one of the most technically demanding aspects of what Jenkins accomplished, and it rarely gets the attention it deserves. Switching from organic to sintered metallic friction materials isn't simply a matter of installing stronger parts. Different friction materials have different engagement characteristics, different heat management profiles, and different wear patterns. Sintered metallic clutches engage harder and more abruptly than organic materials, which is exactly what you want for a high RPM race transmission, but which requires careful calibration of the hydraulic system to manage the engagement precisely enough that you're not breaking other components or causing inconsistent shift. The integration of the new friction material with the modified hydraulic system was a complex optimization problem, and Jenkins worked through it with the same methodical patience he brought to every other aspect of the development. The torque converter work is similarly underappreciated. Modern racers have access to an enormous range of converter options from specialized manufacturers who understand these applications deeply. In 1975, the knowledge base for custom converter development was far thinner. Jenkins was working with converter builders to develop specifications that had no real precedent for an application that required performance characteristics that no production converter was designed to provide. The stator angle modifications he worked through affected the converter's ability to multiply torque at launch and then transition to efficient coupling at speed. Getting that balance right for a specific engine combination, rear gear ratio, and track surface condition required iterative testing and a strong conceptual model of what the converter was doing at each phase of a run. Now let's talk about something that rarely comes up in discussions of Jenkins's work, but that I think is central to understanding why his approach produced such durable results. Jenkins was fundamentally a systems thinker in an environment that rewarded component-level thinking. Most of his competitors, even the excellent ones, thought about their cars as collections of parts, each of which could be improved individually. If the engine needed more power, you worked on the engine. If the transmission was a weak link, you worked on the transmission. This is a reasonable way to approach the problem, and it produced real results for a lot of teams. Jenkins thought differently. He understood that the car was a system, and that a change in any one element changed the optimal configuration of every other element. When he raised his shift point, he didn't just modify the transmission. He recalculated the ideal rear gear ratio. He revisited the cam profile to ensure the engine would actually make power at the new operating range. He reconsidered tire selection to manage the effective final drive ratio under load. He examined the aerodynamic situation at the speeds where his approach would show the greatest advantage. Every change he made to one system prompted a complete evaluation of whether other systems needed adjustment to remain optimally configured for the new overall approach. This kind of integrated thinking is genuinely difficult. It requires holding a complete model of the car as a system in your mind while simultaneously digging into the specific details of individual components. It requires resisting the temptation to optimize individual parts in isolation when isolated optimization doesn't necessarily produce system-level improvement. And it requires a willingness to revisit decisions you've already made and feel confident about when new information suggests they need revision. Jenkins did all of this consistently and systematically over years of development work. The wins were the visible output of that invisible capability. The impact on transmission builders as a professional community is a thread of this story that deserves more direct attention. Before Jenkins demonstrated what was possible, the community of people who built racing transmissions was relatively stable, operating on techniques and knowledge that had evolved incrementally over years. Jenkins's results created an immediate and urgent demand for a different kind of expertise. Builders who could understand and implement high RPM modifications were suddenly far more valuable than those who couldn't. The knowledge hierarchy within the profession reorganized itself around a new set of capabilities that hadn't existed as a formal discipline just a few years earlier. This created interesting dynamics within the builder community. Some experienced builders adapted quickly, drawing on deep foundational knowledge to understand Jenkins's modifications and implement them effectively. Others found the conceptual shift too large to make in time to remain competitive. New builders emerged who had grown up learning the modified power glide as their baseline rather than as a departure from standard practice. These new builders sometimes surpassed older, more experienced hands precisely because they had no existing mental model to overcome. They learned the high RPM system as the system, not as a radical modification of something else. The parts supply ecosystem transformed in parallel. Manufacturers who had been producing power glide components primarily for the replacement market found themselves suddenly supplying parts optimized for applications their engineers had never anticipated. The specifications for clutch packs, bands, valve body components, and pressure regulators that had been essentially stable for years were suddenly being challenged and in many cases completely replaced by purpose-built racing alternatives. Companies that responded quickly built strong positions in the new market. Those that moved slowly found themselves supplying parts to teams that were losing to competitors using superior alternative. Here's what's particularly striking about the scope of change Jenkins triggered when you look at it from a manufacturing perspective. The Powerglide had been in production since 1950. By 1975, the aftermarket for replacement parts was mature, well-established, and operating on stable specifications. Jenkins's work didn't just create demand for better parts. It created demand for fundamentally different parts, made from different materials, to different specifications, for applications that the existing supply chain had no framework for understanding. Meeting that demand required not just new manufacturing runs but new engineering work, new material sourcing, and new quality control standard. All of that happened because one racer in Ohio started shifting later than everyone thought was reasonable. The ripple effects of Jenkins's Powerglide innovations continued to spread through motorsports in ways that became harder to trace directly to their origin but were nonetheless real. The mindset shift, the acceptance that factory specifications are starting points rather than limits, that conventional wisdom should be tested rather than simply trusted, that average performance across a run matters more than peak performance at any instant, these ideas moved through the racing community and shaped how serious development teams in multiple disciplines approached their work. Consider what happened in NASCAR during the same general period. Teams there were grappling with their own version of the same fundamental question: how do you extract more performance from equipment that everyone else has access to? The specific answers were different because the application was completely different. But the investigative framework, measure everything, test assumptions rigorously, think in systems rather than components, was the same framework Jenkins had demonstrated was productive. Whether individual NASCAR engineers and crew chiefs were directly influenced by what Jenkins did in Pro Stock or arrived at similar methods independently is less important than recognizing that the same approach was producing results across different racing contexts simultaneously. Road racing during this period was also undergoing its own transformation in terms of how teams approach development work. The rise of more sophisticated data acquisition, more rigorous testing methodologies, and more systematic approaches to setup optimization reflects the same broader shift in how racing professionals thought about their work. Jenkins was part of that shift, contributing to it from his specific vantage point in pro stock drag racing and influencing others who encountered his approach and found it compelling. The modern pro stock car, when you look at it carefully, is in many ways a direct descendant of what Jenkins built in the mid-1970s. The transmissions used in today's pro stock competition are still fundamentally based on the Powerglide architecture, though they share little with the original beyond the basic two-speed planetary design. Every other element has been custom engineered for the specific demands of the application. The shift points are higher than Jenkins ran, the materials are more exotic, the tolerances are tighter, the instrumentation is vastly more sophisticated. But the underlying philosophy is identical. Keep the engine in its power band. Optimize average power across the run. Think about the drivetrain as an integrated system. The people building those modern transmissions, the top specialists in the field, will tell you that Jenkins's work established the conceptual foundation they're building on. They're using better materials and better tools to go further in the direction Jenkins pointed. The direction itself hasn't changed. What has changed is the complexity of the environment in which that work happens. Modern pro stock rules are significantly more restrictive than they were in Jenkins's era, partly in response to the escalating performance that his kind of innovation made possible. The sanctioning body has had to continuously update its technical regulations to manage the performance envelope within bounds that keep competition meaningful and equipment costs manageable. This is a familiar dynamic in motorsports, where innovation drives performance that drives regulatory response that redirects the next round of innovation. Jenkins was a significant accelerant in that cycle during the period when he was actively developing. Here's the thing about the regulatory response that's worth understanding. When rules tighten in response to innovation, they don't eliminate the value of deep technical understanding. They redirect it. The teams that continue winning after a significant rules change are usually the ones with the deepest fundamental knowledge, because they can find the performance within the new constraints faster than those who were relying more heavily on a specific technical advantage that the new rules eliminate. Jenkins's approach, building complete understanding of how the system works rather than just implementing tricks that happen to produce results, is exactly the kind of foundation that survives regulatory change. The financial dimension of what Jenkins pioneered is something that contemporary accounts often underemphasized, but that shaped how the sport developed in important ways. The cost of running a high RPM powerglide program at the level Jenkins operated, factoring in parts consumption, machine work, dyno time, and the inevitable development failures, was substantial. This created a meaningful barrier to entry for teams that couldn't match the investment. At the same time, it created an opportunity for teams that could manage the cost efficiently, because efficiency in parts usage and development process translated directly to competitive advantage. Jenkins was notably efficient. His disciplined maintenance schedules and rigorous testing meant that he got more competitive runs per dollar of parts investment than teams that were reacting to failures rather than preventing them. The knowledge economy that developed around Jenkins's innovations also had financial implications that extended beyond the racing teams themselves. Engine builders who understood the complete system Jenkins had developed could charge premium rates for their work. Transmission specialists who could build a powerglide to Jenkins-derived specifications became highly sought after and could command significant compensation. The knowledge itself had market value, and the people who possessed it benefited accordingly. This is a pattern that repeats across every field where genuine expertise creates measurable competitive advantage. Now, stepping back from the specific technical and historical details to look at what this story actually means for anyone who's interested in performance, engineering, or innovation in any context, the clearest lesson is about the relationship between understanding and result. Jenkins got better results than his competitors not because he had better basic resources, though his shop was well equipped for its era. Not because he worked harder, though he certainly worked hard. But because he understood the system he was working with more completely than anyone else. Complete understanding let him identify the leverage point that everyone else had missed. And identifying that leverage point produced results that seemed impossible from the outside. This pattern, deep understanding revealing a non-obvious leverage point that produces dramatic results, is not unique to drag racing transmissions. It appears across engineering, science, business, and virtually every other field of competitive human endeavor. The specific domain changes. The pattern doesn't. What Jenkins demonstrated at National Trail Raceway in the mid-1970s was a specific instance of a general principle that applies wherever people are competing on the basis of how well they understand and exploit the systems available to them. The human story underneath all the technical detail is ultimately about intellectual courage. Jenkins had done the math. He had run the test. He had built the evidence. But standing in the staging lane with an engine wound to 8,500 revolutions per minute in first gear, while every experienced voice around you is certain you're about to destroy something expensive and possibly dangerous, still requires a specific kind of nerve. The nerve to trust your own analysis over collective consensus. The nerve to look wrong in front of people you respect until the timing slip proves you right. That combination of intellectual rigor and personal conviction is rarer than raw intelligence or raw talent, and it's what makes stories like Jenkins's worth studying and remembering. So as you watch modern drag racing, with its sophisticated data systems and exotic materials and computer-controlled everything, remember that the philosophical foundation underneath all of it was established in significant part by a man in Ohio who simply refused to accept that shifting at 6,500 revolutions per minute was correct just because everyone said so. He asked a better question, followed the evidence honestly, and changed the sport forever. The equipment has changed almost beyond recognition. The approach that drives the best results still looks remarkably like what Jenkins was doing in that small shop nearly 5 decades ago. What's the 8,500 revolutions per minute shift point in whatever you're building, studying, or competing in? What accepted wisdom are you following because everyone follows it, rather than because you've tested it against reality and found it sound? Drop that in the comments below, because honestly some of the most interesting conversations that happen in this community start exactly there. And if you want more deep dives into the engineering decisions and the people behind them that shaped automotive history in ways that most people never hear about, you know what to do. What if I told you a crew chief once hid a nitrous oxide system inside a suspension component so perfectly that NASCAR spent 7 hours tearing the car apart and still couldn't find it? 7 hours. Cutting torch in hand. Bill France Jr. himself standing there, furious, threatening to slice the car into pieces the size of a silver dollar. And they still missed it. That's not just a cheating story. That's a masterclass in engineering, deception, and the kind of audacious, borderline criminal creativity that defined an entire era of American motorsport. And here's the thing, when they finally did find it, the man who designed it didn't get caught. He confessed. Not because he was scared. Because someone was about to get hurt. This is automotive ancestry, and I spend way too much time thinking about the technical genius hidden inside NASCAR's most infamous cheating scandals. If you're someone who loves the untold engineering stories behind motorsport's wildest moments, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Look, before we get into the device itself, before we talk about the wedge bar and the nitrous and the moment Mario Rossi walked up to Bill France Jr. and said 5 words that rewrote NASCAR's rulebook forever, we need to set the scene properly. Because without understanding the world this happened in, you'll think this is just a story about cheating. It's not. It's a story about the collision between human ingenuity and institutional control, played out at 190 miles per hour in front of 100,000 screaming fans. And it starts on the morning of February 8, 1976, at Daytona International Speedway. The air smells like burnt rubber, racing fuel, and ambition. In garages stretching the length of a football field, some of the greatest mechanical minds in American motorsport are doing what they do every qualifying morning. Lying, improvising, and looking for speed in places nobody else has thought to look yet. That's the context. That's the culture. And that's exactly what made what Rossi was about to do both inevitable and extraordinary. Now, you might be thinking, wasn't cheating in NASCAR just, normal back then? And here's what most people don't realize. It wasn't just normal. It was practically an art form with its own hierarchy of respect. Teams weren't just bending rules. They were rewriting the entire concept of what a rule even meant. This was the era Bill France Sr. used to call creative interpretation, where the rulebook was written in English but read in a completely different language by the crew chiefs who'd been living inside these cars since childhood. The sport had exploded in popularity through the early 1970s. Television was bringing stock car racing into living rooms from Georgia to California. Prize money was climbing. The Daytona 500 purse had grown from $176,000 in 1970 to over $360,000 by 1976. That's nearly $2 million in today's money. Careers, sponsorships, entire livelihoods rode on the difference between starting 3rd and starting 23rd. You think people weren't going to get creative? Come on. The cars themselves were still theoretically based on production vehicles, but by 1976 that relationship was getting pretty loose. Body panels were acid-dipped to shed weight. Frames were reinforced with custom welds that no factory engineer ever drew. Engines were blueprinted and balanced to tolerances the assembly line never imagined. That Monte Carlo Darrell Waltrip drove looked like something you could drive off a Chevrolet lot from 50 feet away. Get any closer and you were looking at a purpose-built racing machine capable of sustaining speeds north of 180 miles per hour for hours at a time. NASCAR's technical inspection team, led by the legendary Bill Jenkins, was in a permanent arms race with these crew chiefs. Every single race weekend brought new innovations designed to operate in the gray zones of the rulebook. Teams offset body panels by fractions of an inch. They used fuel additives that technically weren't prohibited because nobody had thought to ban them yet. One team famously built an oversized fuel tank with a basketball inside. Inspectors measured capacity with the ball inflated. It passed. During the race, they deflated it for extra fuel. Brilliant. Illegal. Brilliant. But even in that environment, nobody had ever tried hiding a pressurized nitrous oxide system inside a load-bearing suspension component. Nobody had even come close to thinking of it. Until Mario Rossi. Here's where we need to talk about the device itself, because the engineering is genuinely remarkable. And I don't say that to glorify cheating. I say it because understanding how this thing worked is what makes the story worth telling. The wedge bar, sometimes called a spring jack bolt, was about as unglamorous a piece of racing hardware as you could find. It was a threaded rod that ran through the rear suspension, connecting to the spring perch. Turning it adjusted the car's cross-weight balance, raising or lowering one corner to change how weight transferred through corners. Every single NASCAR car on every single track had one. It was the last thing any inspector would look at suspiciously because it was the most boring component in the entire car. A roughly 1.25-inch diameter steel rod, about 18 inches long. Mundane. Invisible. Perfect. Rossi didn't just hollow it out and shove some tubing inside. That would have been obvious to anyone who knew what they were looking for. What he actually did was design and fabricate a fully functional, pressure-rated storage cylinder that also performed its original job as a suspension adjustment component. The walls were machined from high-strength steel tubing, thick enough to contain 900 psi of pressurized nitrous oxide while still functioning as a legitimate load-bearing part of the car. After accounting for wall thickness and structural requirements, the internal volume came to approximately 15 cubic inches. At 900 psi, that's enough nitrous oxide for roughly 10 to 12 seconds of full flow injection. On a 2-lap qualifying run at Daytona, that's exactly what you need. Not a drop more, not a drop less. This was precision engineering applied to deception. The release mechanism was where Rossi's thinking really separated itself from anything that had come before. He ran a microbore stainless steel line hidden inside the wedge bar's adjustment threads, completely invisible during any normal inspection. That line connected to a modified carburetor spacer plate with passages drilled at precise angles to inject nitrous directly into the intake airflow. The activation system was wired into the radio push-to-talk button. Hold it down for 3 seconds while in 4th gear and nitrous would flow. From the outside, from the spotter stand, from the NASCAR official standing 3 feet away from the car, Waltrip was just talking to his crew. That's all. Just a driver communicating with his pit box. Nothing to see here. Now let's talk about why nitrous oxide works, because this matters for what happens next. N2O breaks down at combustion temperatures, around 570 degrees Fahrenheit, splitting into nitrogen and oxygen. That released oxygen allows you to burn more fuel. More fuel plus more oxygen equals more power. The chemical reaction happens fast, violently fast, and in a racing engine already operating at the absolute edge of detonation, nitrous is like pouring jet fuel into a blowtorch. The 358 cubic inch small block Chevrolet in Waltrip's Monte Carlo was producing approximately 625 horsepower on racing gasoline under normal circumstances. With Rossi's system engaged, internal calculations suggested they were seeing bursts of 750 to 775 horsepower. That's a 20 to 25% power increase at the literal push of a button. Here's a number that puts that in perspective. At Daytona's high speeds, aerodynamic drag increases exponentially. The difference between running 185 miles per hour and 190 miles per hour requires roughly 50 additional horsepower just to overcome air resistance, just to punch through the air faster. That extra 125 to 150 horses from the nitrous system wasn't just giving them a speed advantage. It was giving them a category-redefining advantage. The kind of advantage that takes a car from top 15 qualifying to pole position territory. And that's exactly what they were chasing. Nitrous had been explicitly banned since 1968 after Junior Johnson was caught using it at Memphis. So Rossi knew exactly what he was risking. This wasn't a gray area. This wasn't creative interpretation. This was deliberate, premeditated, sophisticated cheating in the sport's most important event. The penalties, if caught, would be severe. Suspension, massive fines, potentially criminal charges, certainly the end of careers. Rossi had tested the system dozens of times in the shop, checking every connection for leaks, monitoring pressure drops, looking for any sign that might give it away during inspection. He was confident. He was ready. And on the morning of February 8, 1976, everything was in place. The wedge bar had been installed the night before, pressurized and sealed. The carburetor spacer was torqued to spec, its hidden passages aligned with micrometer precision. The activation switch was wired and tested 3 times. Waltrip had been briefed on exactly when and how to use it. Wait until the back straight on the first lap. Hold for 3 seconds, then release. Save the rest of the charge for the trio valve on lap 2. During morning practice, Waltrip turned consistent laps at 183 miles per hour. Good enough for a top 15 starting position, but nothing that raised eyebrows. A.J. Foyt was running 185. David Pearson was hitting 184. Richard Petty was struggling with an overly tight condition, only managing 181. Nobody was paying special attention to the number 88 Chevrolet. Digard Racing was quick, but not suspiciously so. That was exactly the plan. Then came qualifying. Waltrip rolled onto Daytona's high banks at 2:47 in the afternoon under overcast skies with temperatures sitting in the low 60s. Near-perfect conditions for horsepower, dense air, cool intake charges. The kind of afternoon where engines breathe deep and run hard. He took the green flag and accelerated through turns 1 and 2, the Monte Carlo's engine singing at 7,800 revolutions per minute, a sound that crew chiefs read like a doctor reads a heartbeat. Down the back straight, Waltrip pressed and held what looked, to every observer, like his radio button. Inside the wedge bar, a solenoid valve snapped open. 900 psi of liquefied nitrous oxide rushed through the hidden stainless line, expanded through the carburetor spacer passages, and mixed with the incoming air charge in a fraction of a second. The engine note changed instantly. Not gradually. Instantly. From a sharp, familiar bark to something deeper, angrier, more urgent. The tachometer needle jumped without a gear change, climbing 500 revolutions per minute in less than a heartbeat. Waltrip's head snapped back against the headrest as the Monte Carlo accelerated with a violence that felt completely different from normal power. Like the difference between pushing a door open and having it kicked in from the other side. Turn 3 arrived faster than it ever had before. Waltrip had to brake earlier, harder, but the speed carried beautifully through the corner and onto the trio valve. As the car straightened, he triggered the system again, this time prepared for it, holding the wheel absolutely steady as the Monte Carlo rocketed past the start-finish line. The scoring tower lit up. 187.477 miles per hour. 2 miles per hour faster than morning practice. Fast enough for the provisional pole position. Lap 2 was even better. With 1 lap of experience, Waltrip triggered the nitrous earlier, held it longer, and let the car find its own line through the banking. The Monte Carlo felt like it was straining against gravity itself, front end going light over Daytona's subtle surface undulations. Through the trio valve with the system engaged and the engine screaming past 8,200 revolutions per minute, Waltrip crossed the stripe at 188.91 miles per hour. In the Digard pit area, Mario Rossi stood with his arms crossed and his expression completely, deliberately neutral as crew members exploded around him. They'd just put their car on the provisional pole for the Daytona 500. But Rossi wasn't celebrating. He was watching the NASCAR officials already moving toward their garage. Because he knew the real test was only beginning. This is where it gets really interesting. Within minutes of Waltrip coasting back to the garage, NASCAR inspectors arrived in force. Led by Bill Gazaway and technical director Dick Beatty, they immediately impounded the Monte Carlo, cordoned it off with officials, and began the inspection process. They started with the obvious. Fuel samples were drawn and tested for illegal additives or elevated octane boosters. Clean. Engine displacement was checked against the 358 cubic inch maximum. Legal. Cam timing was verified. Valve spring pressures were measured. Everything within spec. But Gazaway had been doing this for decades, and his instincts were screaming. No car gains 5 miles per hour between practice and qualifying without help. That kind of jump doesn't happen from a better driving line or a favorable wind gust. Something was on that car. He ordered a complete teardown. The intake manifold came off first, inspectors looking for hidden passages in the runners or modified plenum chambers. Nothing. The cylinder heads were pulled and measured for illegal porting or oversized valves. Legal. The exhaust headers were removed and their dimensions checked against spec. Stock. 4 hours into the inspection, they had found absolutely nothing. The car was passing every single test, and the more it passed, the more suspicious everyone got. Because in NASCAR in 1976, a car that passed every test after running that fast wasn't innocent. It was just better hidden than anything they'd seen before. Bill France Jr., NASCAR's executive vice president and the man who would eventually become the sport's most powerful figure, arrived at the inspection area personally. This almost never happened. France showing up in the inspection bay meant the situation had escalated beyond normal channels. He'd grown up watching his father build this sport from dirt tracks and moonshiner culture. He'd seen every trick, every innovation, every attempted deception in 30 years of racing. And standing there watching his inspectors work through that Monte Carlo piece by piece, he could feel it. Something was wrong. He just couldn't find it. Here's what most people don't realize about that inspection. France's team wasn't just looking casually. They were systematic, methodical, and increasingly desperate. They cut the braided steel fuel lines open looking for hidden secondary delivery systems. Nothing. They drained 12 quarts of Valvoline racing oil and pulled the oil pan, checking for hidden compartments that could inject power-adding chemicals into the engine. Clean. They drilled inspection holes in the main roll cage tubes, checking for hidden fuel cells, a trick teams had used before. Solid steel throughout. 6 hours in, France was past frustrated and into a cold, focused fury. The lap times were evidence. 188.91 miles per hour didn't happen by accident. It didn't happen because Waltrip had a particularly good day or because the wind was favorable. It happened because someone had done something to that car that his entire inspection team, with 6 hours of work, could not identify. That's when France made his famous threat. Standing in the inspection bay with Rossi, Waltrip, and team owner Bill Gardner watching, he looked at the car and said, clearly and without any drama, that he would cut this car into pieces the size of a silver dollar if that's what it took. He meant every single word. Mechanics arrived with cutting torches and plasma cutters. They were going to start with the frame rails, work through the floor pans, and then begin systematically sectioning the suspension component. Mario Rossi stood there and watched them prepare to destroy months of work, hundreds of thousands of dollars in equipment, and the car that had just run the fastest qualifying lap of his career. And then he thought about something that changed everything. His hidden nitrous system was pressurized to 900 psi. That's roughly the same pressure as a fully charged scuba tank. If a cutting torch hit that wedge bar without any warning, without anyone knowing what was inside, the rapid expansion of superheated gas inside a steel tube could create an explosion violent enough to seriously injure or kill whoever was holding that torch. Maybe kill whoever was standing nearby. Rossi might have been willing to gamble his career. He was not willing to gamble a person's life. At 9:35 in the evening, after 7 hours and 35 minutes of inspection, Mario Rossi walked across the inspection bay floor and stopped in front of Bill France Jr., and he said 5 words. It's in the wedge bar. France's expression ran through 3 stages in about 3 seconds. Confusion, because why would anyone say that without context? Realization, because a wedge bar is a suspension component and suspension components aren't checked for hidden systems. And then fury, cold and precise, the kind that comes not from surprise but from finally understanding the depth of what you've been dealing with. The wedge bar. In 30 years of NASCAR technical inspection, nobody had ever thought to examine one for anything beyond its basic structural function. It was the last component anyone would look at. It was, of course, the perfect place to hide something. Even knowing exactly what they were looking for, it took inspectors 20 minutes to locate the release valve and the hidden stainless lines inside the wedge bar. The engineering was that clean, that precise. When they finally cracked it open, carefully, after Rossi specifically warned them about the pressure inside, France just stood there looking at it. The machining on the internal cylinder. The microbore stainless line nested perfectly inside the adjustment threads. The solenoid valve so small and clean it barely looked like a component at all. He didn't say anything for a long moment. And then he shook his head, and that single gesture said more than any fine or suspension that followed. Now, you might be thinking, wasn't Rossi's confession the real mistake? Wouldn't they have eventually missed it? And here's the thing, maybe. If France had followed through with the cutting torches and nobody had warned about the pressure, the wedge bar might have been sectioned and the nitrous might have been attributed to a hollow component used for weight reduction, illegal, but not nearly as serious as a hidden injection system. The full sophistication of the device might never have been understood. Rossi's confession didn't just reveal the cheat. It revealed the depth of the engineering behind it. And that made the response from NASCAR proportionally more severe. The penalties came quickly. Waltrip's qualifying times were disallowed entirely. The team was fined $7,500, equivalent to roughly $40,000 in today's dollars. Rossi received an indefinite suspension from NASCAR competition, later reduced to 90 days after appeals. Bill Gardner had to submit a formal written apology to NASCAR's governing body. But those immediate penalties were almost secondary to what happened next, because the wedge bar incident didn't just cost Junkyard Racing a pole position. It fundamentally changed how NASCAR thought about technical inspection forever. Within a week of the incident, NASCAR issued a technical bulletin that required all wedge bars to be either solid steel or completely filled with foam, eliminating any internal space that could conceal a pressurized system. But that was just the surface-level response. The deeper change was in philosophy. Before February 1976, NASCAR's inspection process operated on a model of specific prohibition. You checked for the things you knew people were trying to do. You measured the parts you knew people were modifying. You looked in the places you'd found cheating before. After the wedge bar, all of that changed. The new model assumed that cheating was happening somewhere, in some component, using some method that hadn't been seen yet. And the job of inspection was to work backward from that assumption to find it. Gary Nelson, who would go on to become one of NASCAR's most important technical officials, later reflected on what Rossi's device revealed about inspection philosophy. He said that Mario Rossi showed everyone that the best place to hide something illegal was inside something legal. Not just in a legal car. inside a specific, individual legal component that performed its required function while also doing something completely different. That insight rewrote the entire framework of how NASCAR approached technical inspection for the next 2 decades. The inspection process that typically ran 2 hours before 1976 expanded to 4 and 5 hours as new categories of components were added to the mandatory teardown list. Other crew chiefs absorbed the lesson, though not in the way Rossi intended. Nobody was going to try hiding nitrous in suspension components again, because now NASCAR was specifically checking for exactly that. But the conceptual framework, the idea that concealment worked best when it disguised itself as something completely ordinary, inspired a generation of innovation. Teams began hiding tungsten ballast weights inside hollow body panel supports to manipulate weight distribution without detection. They used selective chemical treatments on metal to reduce weight in specific areas while maintaining structural appearance. One crew chief built a complete false floor section into the car that contained a secondary fuel cell, invisible because nobody thought to verify the interior dimensions against a baseline measurement. The game continued. It just moved to new territory. Here's where the story gets genuinely fascinating from an engineering standpoint. Because what Rossi built in 1976 with hand tools, a lathe, and a machinist's intuition is remarkably close to what modern teams attempt with computational design tools and materials science. The fundamental challenge hasn't changed. You're trying to create a component that performs 2 distinct functions simultaneously, one legal and visible, one illegal and hidden, without any external indication that the second function exists. Modern NASCAR's response to this challenge is essentially total information. Laser measurement systems that map every surface of the car in 3 dimensions. Computerized templates checked against baseline specifications stored in a digital database. Sealed and tagged components with tamper-evident systems. Weight checks performed on individual subsystems rather than just the complete car. The wedge bar incident was the first major demonstration that NASCAR's inspection model was built on an assumption that couldn't survive contact with truly creative engineering. The assumption was that cheating would be found in places that had been checked before, in components that had been modified in known ways, using methods that had been attempted previously. Rossi's device violated all 3 of those assumptions simultaneously. He used an unchecked component, modified in a completely novel way, using a method that had never been attempted in that form in NASCAR. He essentially found the 3-dimensional blind spot in a 2-dimensional inspection process. Bill France Jr. understood this immediately. That's why the threat to cut the car into silver dollar pieces wasn't just frustration. It was the recognition that his existing inspection framework had failed completely, and the only remaining option was total deconstruction. Brute force applied to a problem that required intelligence to solve. The irony is that brute force was about to succeed, not because it was better than Rossi's engineering, but because Rossi valued human safety more than his own protection. Now let's talk about what happened after. Because the story doesn't end in the inspection bay on February 8. The 1976 Daytona 500 went on as scheduled, with David Pearson winning from the Wood Brothers Mercury after leading 65 of 200 laps. Richard Petty finished second. Waltrip, starting from the back after losing his qualifying time, worked his way through the field and finished respectably, though that result is largely forgotten. What nobody forgets is the wedge bar. That inspection bay conversation between Rossi and France became one of the most retold stories in NASCAR paddock culture, passed down through generations of crew members the way other trades pass down cautionary tales and origin myths simultaneously. Darrell Waltrip went on to become a 3-time NASCAR Winston Cup champion in 1981, 1982, and 1985. He became one of the sport's most beloved figures and one of its most recognized broadcast voices. He's told the wedge bar story hundreds of times across those decades, and it never loses its shape. He's always clear that he understood what was in the car, that he activated the system on purpose, and that he has enormous respect for the engineering that went into it. His line about Rossi thinking in a different zip code from the rulebook has become something of a shorthand for a specific kind of lateral creative thinking that NASCAR's culture both celebrates and fears. Mario Rossi returned to NASCAR after his 90-day suspension and continued working in the sport through the 1980s. He crew chiefed for several competitive teams, won races, and built a legitimate reputation as one of the most technically sophisticated minds in the garage. But he was never not the wedge bar guy. In the rare interviews he gave about it, his feelings were complicated in ways that feel honest. Pride in the engineering because what he built was genuinely remarkable. Regret about the ethical dimension because it undermined the competitive integrity of an event that a lot of people cared deeply about. And a persistent sense that the line between creative interpretation and cheating was drawn differently by different people at different moments. Look, that last point matters more than it might seem, because it gets at something fundamental about what motorsport actually is and what it's always been. Racing has never been purely about who can drive fastest. It's been about who can find speed in places nobody else has looked yet, who can interpret rules in ways that create competitive advantage, who can outthink the competition not just on the track but in the garage at midnight when nobody's watching. That tension is built into the sport's DNA. It's why the technical regulations in NASCAR are now hundreds of pages long when they were once a few paragraphs. Every page of that rulebook represents a specific innovation that someone attempted, often successfully, before NASCAR closed the door. The wedge bar takes up maybe 2 lines in that rulebook today. Wedge adjustment bars shall be solid steel or polymer filled with no internal void space. 2 lines. Behind those 2 lines is 7.5 hours of inspection, the threat of plasma cutters, a 5-word confession whispered in a fluorescent-lit garage, and one of the most elegant pieces of deceptive engineering in motorsport history. Here's what most people don't realize about the long-term impact. The wedge bar incident wasn't just important for what it revealed about cheating. It was important for what it revealed about the relationship between innovation and regulation in competitive environments. The same mental framework that produced the hidden nitrous system, the willingness to look at a component's function and ask whether that function could be replicated in a form that also did something else, is the same framework that drives legitimate engineering innovation. When engineers at a major manufacturer look at a transmission housing and ask whether that space could also serve as a structural element that eliminates a separate bracket, they're thinking exactly the way Rossi thought. The difference is purely about which side of the rulebook you're operating on. And the people who are best at legitimate engineering innovation are often the same people who would have been outstanding at the dark arts version in a different context. NASCAR understood this, eventually. The sports technical department has hired people with backgrounds in exactly this kind of systems-within-systems thinking, because you can only catch cheating if you can imagine it first. Gary Nelson's career trajectory, from innovative crew chief to NASCAR's technical director, is essentially that insight institutionalized. The wedge bar itself, the actual physical device that Rossi machined and pressurized and installed in Darrell Waltrip's Monte Carlo that February morning, still exists. After the inspection concluded, it was retained as evidence during the appeals process. It was supposed to be destroyed per standard procedure for confiscated illegal component. It wasn't. It ended up in Bill France Jr.'s personal collection, which says something interesting about how France himself processed the incident. The man who threatened to cut the car into silver dollar pieces kept the most important piece of evidence as what? A trophy? A reminder? An object lesson? Maybe all 3. Today that wedge bar sits in the NASCAR Hall of Fame archives in Charlotte, North Carolina. It's not on public display. It's cataloged and preserved in climate-controlled storage as an artifact of the sport's formative years. There's something almost poetic about that. The device that never should have existed, that was built to be invisible and undetectable, that was confessed to under the pressure of a cutting torch, that changed how an entire sport policed itself, preserved in a museum archive. Not celebrated, exactly. Not condemned. Just kept because it's too significant to throw away and too complicated to explain to a general audience in a wall placard. It exists in that same ambiguous space that the whole incident occupies in NASCAR's cultural memory. Too impressive to dismiss, too dishonest to celebrate, too important to forget. Modern NASCAR inspection would have found Rossi's device in minute. The whole car 3D laser scan would have flagged the wedge bar's internal geometry as inconsistent with a solid component. The weight check would have shown a discrepancy between what a solid steel bar of those dimensions should weigh and what the actual component weighed. The pressure sensor sweep that teams now undergo for certain components would have lit up immediately. But here's the thing about that. The sophistication of modern inspection didn't emerge from NASCAR's own innovation. It emerged from the arms race that incidents like the wedge bar forced. Every layer of the current inspection system is a response to something someone tried. The technology advanced because the cheating advanced first. Which brings us back to where this story actually lives, in that strange territory between genius and wrongdoing where the most interesting moments in any competitive sport exist. The wedge bar incident was wrong. It was a deliberate, premeditated attempt to gain an unfair advantage in the sport's most prestigious event using a sophisticated device hidden inside a component specifically chosen because inspectors would never look there. It violated not just NASCAR's technical regulations but the basic principle that competition should be decided by skill, preparation, and legitimate innovation rather than the ability to conceal an illegal advantage. All of that is true. And it's also true that what Mario Rossi built in his shop in the weeks before the 1976 Daytona 500 was a remarkable piece of engineering that revealed a genuine blind spot in NASCAR's inspection philosophy, triggered a fundamental rethinking of how the sport policed technical innovation, and produced a story that people are still telling nearly 5 decades later. This is where it gets really interesting, and I mean this genuinely. The stories that last in motorsport aren't usually the clean victories or the straightforward championship. They're the moments where human creativity, competitive pressure, and institutional authority collide in unexpected ways. The moments where someone does something that makes everyone around them simultaneously furious and impressed. The moments that reveal something true about what competition actually is beneath the surface of the official narrative. The wedge bar is one of those moments. 7 hours of inspection, a cutting torch, 5 words, and a piece of machined steel that rewrote the rulebook. That's a story worth knowing. What's your take on where the line falls between creative engineering and outright cheating in motorsport? Because honestly, different people in that garage that night would have drawn it in different places, and I think that ambiguity is part of what makes the story so persistent. Drop your thoughts in the comments below. And if you want more deep dives into the engineering stories and technical controversies that shaped motorsport into what it is today, subscribe to Automotive Ancestry because there are a lot more stories like this one, and most of them are even stranger than you'd expect. Until next time, keep looking at the parts nobody thinks to check.